Alpha Centauri is 4.2 light-years away. That is 25 trillion miles. And if we left tomorrow on the fastest spacecraft humans have ever built, our descendants would arrive in the year 8,700. Long after every language we speak has evolved into something unrecognizable. Long after the nations that launched the mission have risen, fallen, and been forgotten. The crew that departed would never see the destination. Neither would their children, or their children's children. This is not science fiction. This is the math, the cold, unforgiving arithmetic of interstellar space. Our closest stellar neighbor, the star we can see with the naked eye on a clear night, might as well be on the other side of infinity, because 25 trillion miles is not just far. It is a distance that breaks every assumption we have about travel, about exploration, about what it means to go somewhere and come back. But what if we could go faster? What if we could reach 10% of light speed, screaming through the void at 67 million miles per hour? The trip drops to 42 years, a single human lifetime. One generation, locked inside a steel tube, hurtling through a darkness so complete that Earth becomes a pale blue dot. Then a star, then nothing at all. No rescue, no resupply, no second chances. And at that speed, a grain of sand hits with the force of a nuclear bomb. At that speed, the universe itself becomes a weapon. So why are we talking about this? Why do we keep imagining missions we cannot launch, to places we cannot reach, on timescales longer than recorded history? Because Alpha Centauri is there, and we are here, and the gap between those two facts is the most honest mirror humanity has ever looked into. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We are nowhere near as close to the stars as we think we are. That sounds dramatic, but here's the truth. The nearest star system to Earth, Alpha Centauri, is sitting about 4.25 light-years away, which is a sentence that means absolutely nothing to your brain until you convert it into something your life has given you the tools to understand. 4 light-years sounds neighborly. It sounds like a short hop across the cosmic street. It is not. A light-year is not a unit of time. It is a unit of distance. Specifically, it is the distance light travels in 1 year. And light moves fast, faster than anything else in the universe. It crosses roughly 5.88 trillion miles in a single year. Nothing you have ever seen, touched, or ridden in comes remotely close to that speed. The fastest jet you've ever flown on covers maybe 600 miles per hour. Light covers 186,000 miles per second. You blink, and light has already lapped the Earth 7.5 times. Now take that incomprehensible speed and stretch it across 4 years. That is how far Alpha Centauri is, about 25 trillion miles. Give or take a few 100 billion, which at this scale is a rounding error. 25 trillion miles. Let's sit with that for a moment, because your brain is going to try to skip past it. Most people hear large numbers and their minds glaze over. A billion, a trillion, it all sounds the same after a while. Big, abstract, irrelevant to daily life. But this number is not abstract. It is the only thing standing between humanity and the stars, and it is larger than almost anything your species has ever tried to measure or cross. Here is one way to think about it. The distance from Earth to the Moon is about 240,000 miles. Humans have walked on the Moon. We sent people there in tin cans strapped to controlled explosions, and they came back alive. That trip, which felt monumental in 1969 and still feels monumental today, took about 3 days each way. The moon is the farthest any human being has ever traveled from home. It is also about 100 millionth of the distance to Alpha Centauri. If you could somehow drive a car to Alpha Centauri at highway speed, 60 miles per hour, non-stop, no brakes, no traffic, the trip would take about 47 million years. You would start that drive before the first hominids stood upright. You would still be driving. The Sun is much farther than the Moon. It sits about 93 million miles from Earth. That distance is called an astronomical unit, and it is the baseline measurement astronomers use when talking about anything inside our solar system. 1 AU, Earth to Sun, 93 million miles. It takes light about 8 minutes to cover that gap. If the Sun exploded right now, you would not know for 8 minutes because the light carrying that information has not reached you yet. Alpha Centauri is not 93 million miles away. It is not 930 million miles away. It is roughly 277,600 times farther than the Sun. 277,000 Earths to Suns, lined up end to end, and you still have not reached the nearest star. Pluto, the dwarf planet lurking at the dim edge of our solar system, orbits at about 40 astronomical units from the Sun on average. It takes light over 5 hours to get there. New Horizons, the spacecraft that flew past Pluto in 2015, took 9.5 years to make the trip. And Pluto is still in our neighborhood. It is still, in cosmic terms, right next door. Alpha Centauri is 7,000 times farther than Pluto. Here is another angle. Voyager 1, launched in 1977, is currently the most distant human-made object in existence. It is over 15 billion miles from Earth, flying through interstellar space at about 38,000 miles per hour. It has been traveling for nearly 50 years. It has left the solar system. It is out there in the dark between stars, farther than anything humanity has ever touched. And if you pointed Voyager 1 directly at Alpha Centauri right now and let it coast at its current speed, it would arrive in about 73,000 years. Some sources round that down to around 6,700 years, depending on the exact speed and trajectory assumptions. Either way, the point stands. Voyager 1 will not make it to Alpha Centauri in your lifetime. It will not make it in the lifetime of your civilization. By the time it got there, if it were aimed that way, which it is not, every language currently spoken on Earth would be dead. Every nation would be gone. Every city you know would be dust. Entire epochs of human history would rise and fall and be forgotten, and Voyager would still be coasting through the void, silent and alone, not even halfway there. That is how far 25 trillion miles is. Alpha Centauri is not one star, it is 3, a triple star system. The two largest stars, Alpha Centauri A and Alpha Centauri B, orbit each other in a slow binary dance. The third member, Proxima Centauri, is a small red dwarf that orbits the pair at a much greater distance. Proxima is the closest of the three. It sits about 4.24 light-years from Earth. That is where the 25 trillion mile figure comes from. 4.24 light-years times 5.88 trillion miles per light-year gives you roughly 25 trillion miles. More precisely, about 25.8 trillion. But at this distance, precision feels almost absurd. Proxima Centauri is not a welcoming star. It is dim, barely visible even with a telescope. It is also violent. Red dwarfs like Proxima are known for throwing massive flares, sudden eruptions of radiation and charged particles that blast out into space with enough energy to strip atmospheres off nearby planets. There is a planet orbiting Proxima, called Proxima Centauri b, sitting in what astronomers cautiously call the habitable zone, close enough to the star that liquid water could, in theory, exist on its surface. But whether anything could actually live there under the constant bombardment of stellar tantrums is another question. Still, Proxima b is the closest potentially habitable exoplanet we know of, and it is 25 trillion miles away. For comparison, the next nearest Sun-like star after Alpha Centauri is only about 3 times farther, which tells you two things. 1. The stars are spaced absurdly far apart, even by cosmic standards. And 2. Alpha Centauri really is our best shot. If we cannot reach the nearest star, we cannot reach any of them. The concept astronomers use to describe this problem is called reachability. A destination is reachable if you can get there and back, or at least get there within a time frame that makes the journey meaningful. The Moon is reachable, Mars barely is reachable. The outer planets are technically reachable if you are willing to wait decades and accept that the people who launched the mission will not be the people who see it arrive. Alpha Centauri, by any current measure, is not reachable, not in a human lifetime, not in 10 human lifetimes, not with anything we have built or anything we know how to build. And here is the uncomfortable part. The distance is not the only problem, it is just the first problem, the most obvious one. The one that sits at the front of every conversation about interstellar travel and refuses to move. But even if we could somehow solve the distance, even if we could build a ship fast enough to cover 25 trillion miles in a reasonable amount of time, we would immediately run into a dozen other problems that are just as hard and just as unforgiving: radiation, fuel, life support, navigation, communication. The simple biological fact that human bodies were not designed to spend decades or centuries locked inside a metal tube hurtling through a vacuum. But we are not there yet. Right now, we are still stuck on step 1, the distance itself, 25 trillion miles. And no matter how many ways you try to shrink it, compress it, or talk around it, it does not get smaller. NASA has a habit of describing space distances in language that makes them sound almost casual. Their website will tell you that Alpha Centauri is just over 4 light-years away, as if the word just belongs anywhere near a measurement that large. They will say it is about 25 trillion miles from Earth, the way you might say your cousin lives about 200 miles upstate. The tone is informative, almost cheerful, but the numbers themselves are anything but casual. Think of it this way. If you wanted to build a scale model of the distance between Earth and Alpha Centauri, and you represented Earth as a grain of sand 1 millimeter across, the Sun would be about a marble sitting 10 centimeters away, Pluto would be about 4 meters away, and Alpha Centauri would be sitting 2.7 kilometers down the road. That is the scale we are dealing with. A sandy beach where every grain is a planet, and the next beach is 3 kilometers away. Humans are not wired to think at these scales. Evolution built our brains to navigate forests and rivers and open plains. We are good at estimating distances we can walk in a day. We are decent at imagining trips that take weeks or months, but our intuition falls apart past that. 1 million, 1 billion, 1 trillion. The words stop meaning anything concrete. They become placeholders for big, and yet the universe runs on these numbers. The stars do not care that we find them incomprehensible. They sit where they sit, separated by gulfs of space so vast that light itself, the fastest thing in existence, takes years to cross them. And we are stuck here on a small blue planet, trying to figure out how to bridge a gap that makes the entire history of human civilization look like a rounding error. Voyager 1 is not aimed at Alpha Centauri. It is headed in a completely different direction, drifting toward the constellation Ophiuchus. If it were aimed at Alpha Centauri, and if it could somehow survive the journey, and if anyone were still around 70,000 years from now to receive its signal, it would arrive at a star system that looks almost nothing like ours. No gas giants, no asteroid belt. Just a few rocky worlds orbiting a dim red star that spends most of its time throwing radiation at anything unlucky enough to be nearby. But Voyager was never meant to go to another star. It was built to tour the outer planets, Jupiter, Saturn, Uranus, Neptune, and then coast into interstellar space as a kind of ambassador. A message in a bottle carrying a golden record with sounds and images from Earth, drifting forever through the dark on the off chance that someone, someday, might find it. The fact that Voyager is still functioning nearly 50 years after launch is a minor miracle of engineering. The fact that it will take 70,000 years to travel 4 light-years is a reminder of how far we still have to go. Some people hear these numbers and give up. They decide interstellar travel is impossible and always will be, that the stars are too far, the problems too hard, the physics too unforgiving, and maybe they are right. Maybe the universe has written a speed limit into its laws that no amount of cleverness or determination can bypass. But here is the other side of that. 70,000 years ago, humans were still living in caves. We had barely figured out fire. We had no cities, no agriculture, no written language. The idea that we would one day build machines that could leave the planet, fly past the moon, orbit the sun, and drift into interstellar space would have been incomprehensible. And yet here we are. The distance to Alpha Centauri has not changed. 25 trillion miles today, 25 trillion miles 1,000 years from now. But what has changed, and what could still change, is how fast we can move. Right now, with chemical rockets, the kind we have been using since the 1960s, we are locked into speeds that make interstellar travel a multi-generational fantasy at best. Voyager's 38,000 miles per hour sounds fast until you compare it to the speed of light. Light moves at 670 million miles per hour. Voyager, our fastest spacecraft, is crawling at about 0.006% of light speed. To make Alpha Centauri reachable, we need to go faster, a lot faster. And that brings us to the next problem, the one that makes the distance look almost quaint by comparison. If 25 trillion miles is the wall, propulsion is the sledgehammer we do not have, and the gap between what we can do and what we need to do is so large that it might as well be another 25 trillion miles. Here is the uncomfortable truth. Every rocket ever built, every spacecraft ever launched, every mission that has left Earth's atmosphere and traveled to the moon or Mars or beyond has been powered by fundamentally the same idea. You take something that burns, you ignite it in a controlled explosion, and you use the force of that explosion to push yourself in the opposite direction. It is called chemical propulsion, and it works beautifully for getting off the ground. It works for reaching orbit. It works for sending a probe to Jupiter or a rover to Mars. It does not work, not even remotely, for traveling to another star. Chemical rockets are fast in the way a sports car is fast, impressive relative to a bicycle, irrelevant compared to a jet, and laughably inadequate when the destination is 4 light-years away. The Space Shuttle, when it launched, accelerated to about 17,500 miles per hour to reach low Earth orbit. That is fast enough to circle the planet every 90 minutes. It is not fast enough to leave the solar system in any reasonable time frame. Voyager 1, which we talked about earlier, is moving at around 38,000 miles per hour. That is faster than anything humans have ever built, and it would still take over 73,000 years to reach Proxima Centauri if it were aimed that direction, which it is not. The problem is not that chemical rockets are badly designed, they are not. The problem is physics. Specifically, the problem is a relationship so unforgiving that it has its own name. Rocket scientists call it the tyranny of the rocket equation, and it is one of the main reasons interstellar travel remains firmly in the realm of science fiction. Here is how the rocket equation works. To go faster, you need fuel. The more fuel you carry, the heavier your spacecraft becomes. The heavier your spacecraft, the more fuel you need to accelerate it, which makes it heavier, which requires more fuel. The equation spirals out of control almost immediately. You end up in a situation where the vast majority of your rocket's mass at launch is just fuel, and only a tiny fraction is the actual payload you are trying to send somewhere. The Saturn V rocket that sent astronauts to the moon weighed about 6.5 million pounds fully fueled. The Apollo command module that actually went to the moon and came back weighed about 12,000 pounds. Everything else was fuel and structure that got burned up or discarded along the way. That works fine for a 3-day trip to the moon. It does not scale to a journey across trillions of miles. To reach even a fraction of the speed of light using chemical rockets, you would need so much fuel that the mass of the rocket would exceed the mass of entire planets. Some estimates suggest that to accelerate a single probe to 10% the speed of light, a speed that would get you to Alpha Centauri in about 40 years, you would need a fuel tank larger than Jupiter. And that is just to accelerate. You would need an equally absurd amount of fuel to slow down once you got there, assuming you wanted to stop and look around instead of screaming past at 30,000 kilometers per second. The math does not work. It has never worked. And no amount of engineering cleverness can change the fundamental constraint. Chemical energy, the energy you get from burning hydrogen and oxygen or kerosene or whatever propellant you choose, has a fixed energy density. There is only so much push you can get out of a kilogram of fuel, and it is nowhere near enough. So if chemical rockets are out, what about nuclear propulsion? That idea has been floating around since the 1950s. The concept is straightforward. Instead of burning fuel, you use a nuclear reactor or a nuclear bomb to generate heat, and you channel that heat through a propellant to create thrust. The energy density of nuclear fuel is orders of magnitude higher than chemical fuel. A kilogram of uranium contains millions of times more energy than a kilogram of gasoline. In theory, a nuclear rocket could be dramatically more efficient. In practice, it is still not enough. Nuclear thermal propulsion, the most developed form of the idea, might give you twice the efficiency of the best chemical rockets, maybe 3 times if you push it. That sounds great until you realize it is still nowhere close to what you need for interstellar travel. Going twice as fast as Voyager does not turn a 70,000-year journey into a quick trip. It turns it into a 35,000-year journey, still completely impractical, still far beyond any human lifespan or even any conceivable multi-generational mission. And then there are the engineering problems. Building a nuclear reactor that can survive launch, operate reliably in space for decades, and not irradiate your spacecraft or crew is hard. Building one light enough to actually improve your mass ratio is harder, and building one powerful enough to get you to a meaningful fraction of light speed is, with current technology, impossible. But even if we solved the rocket equation somehow, even if we invented a propulsion system with perfect efficiency and unlimited energy, we would still hit a wall. A wall built not by engineering limitations, but by the structure of the universe itself. That wall is Albert Einstein's theory of relativity, and it is not a suggestion, it is a law. Special relativity, published in 1905, changed the way physicists understand motion. Before Einstein, most scientists assumed that if you kept accelerating an object, it would just keep getting faster indefinitely. Add more energy, go faster. Simple. Einstein showed that this is not how the universe works. As an object accelerates and approaches the speed of light, something strange happens. Its effective mass increases, not because it is gaining atoms or material, but because of the way mass and energy relate to each other at relativistic speeds. The faster you go, the more massive you effectively become. And the more massive you are, the more energy it takes to accelerate you further. At everyday speeds, this effect is negligible. A car moving at 60 miles per hour does not weigh any more than a car sitting still, at least not in any way you could measure. But as you approach the speed of light, the effect becomes dominant. By the time you reach 90% of light speed, your effective mass has more than doubled. At 99%, it has increased by a factor of 7. At 99.9%, a factor of 22. The closer you get to light speed, the more energy you need to squeeze out even the tiniest additional increment of velocity. And at exactly the speed of light, your mass becomes infinite. Infinite mass requires infinite energy, and infinite energy does not exist. This is not a technical limitation. It is not something we will overcome with better technology or more funding. It is a fundamental property of space-time. The speed of light is not just a speed limit. It is a boundary written into the fabric of reality. Nothing with mass can reach it, period. NASA has stated this plainly. Traveling at light speed is an impossibility due to special relativity. Accelerating an object to light speed would take an infinite amount of energy. Those are not exaggerations. Those are the equations talking. The universe has rules, and this is one of them. So even if we could build a propulsion system with perfect efficiency, even if we had access to unlimited fuel, we still could not reach light speed. The best we could do is get close. And close, in this context, still means impossibly far from our current capabilities. Let us talk about energy requirements, because the numbers are staggering. To accelerate a single 1-ton probe to 10% of the speed of light, a speed that would let you reach Alpha Centauri in a little over 40 years, you would need roughly 450,000 terajoules of energy. For context, the entire annual energy consumption of the United States is about 94 million terajoules, so you would need about 0.5% of a year's worth of total US energy output just to accelerate a 1-ton object to 1/10 of light speed. And again, that is just acceleration. Slowing down at the other end requires the same amount of energy all over again. Now scale that up. A probe the size of Voyager weighs closer to 800 kilograms. A crewed spacecraft capable of supporting humans for decades would weigh thousands of tons. The energy requirements explode. You are no longer talking about a fraction of a nation's energy budget. You are talking about energy outputs that rival the total power generation of the entire planet for years on end, all focused on pushing a single object through space. And where does that energy come from? Not from chemical fuel, not from solar panels, not from anything we currently know how to build or deploy at the necessary scale. Some proposals suggest using antimatter, which has the highest energy density theoretically possible. When matter and antimatter collide, they annihilate each other and convert 100% of their mass into energy, according to Einstein's famous equation. But antimatter does not exist naturally in any usable quantity. You have to manufacture it, particle by particle, in giant accelerators, and the process is staggeringly inefficient. Current production rates are measured in nanograms per year. You would need kilograms, maybe tons, to fuel an interstellar mission. At current production rates, it would take billions of years just to manufacture the fuel. There are other ideas. Fusion propulsion, which mimics the process that powers the sun, could in theory provide enormous amounts of energy from relatively small amounts of fuel. But controlled fusion, the kind you can sustain in a rocket engine, remains an unsolved problem. We have been trying to build practical fusion reactors for over 70 years. We are not there yet. And even if we cracked fusion tomorrow, the engineering challenges of turning it into a Starship engine would take decades more. You start to see the pattern. Every solution runs into a wall. Every promising idea reveals a dozen new problems hiding underneath. The distance to Alpha Centauri is enormous. The energy required to cross that distance in any reasonable time is even more enormous. And the technology needed to harness that energy does not exist. Some people look at these numbers and conclude that interstellar travel is impossible, that we are trapped in the solar system not by lack of ambition, but by the laws of physics, that the stars will remain forever out of reach no matter how advanced we become. And they might be right. There is no guarantee that the universe owes us a way to travel between stars. The fact that we can imagine it does not mean it is possible. But here is the thing. The rocket equation is not wrong, but it is also not the only way to move through space. Chemical propulsion has limits, but propulsion itself is just one approach, and relativity does not say you cannot travel vast distances. It just says you cannot do it faster than light. There is a difference. When physicists and engineers talk about interstellar travel today, they are not talking about building bigger rockets or better fuel tanks. They are talking about rethinking the entire problem from the ground up. They are looking at ideas that sound like science fiction because, frankly, that is all we have left. Conventional approaches do not work, so the only options remaining are unconventional ones. There are concepts on the table that bypass the rocket equation entirely by not carrying fuel at all. Ideas that use external energy sources beamed from Earth or harvested from the environment to push a spacecraft forward. There are proposals that take advantage of relativistic effects to make the journey shorter from the perspective of the travelers, even if it still takes decades or centuries from the perspective of Earth. There are even wilder ideas that involve bending space-time itself, creating shortcuts through the universe that sidestep the distance problem altogether. Some of these ideas are grounded in real physics. Others are purely theoretical, balanced on the edge of what the equations allow, and a few are probably nonsense dressed up in equations. But the fact that serious scientists are exploring them tells you something important. The conventional path is closed. If we are going to reach the stars, it will not be by doing what we have always done, only better. It will be by doing something we have never done before. Something that looks impossible until the moment it is not. The gap between where we are and where we need to be is vast, but it is not infinite. Infinite is traveling faster than light. That is off the table. Everything else is just hard, very hard, absurdly hard, but not fundamentally impossible. There is a difference, and that difference matters. Chemical rockets took us to the moon. They will not take us to Alpha Centauri. Nuclear propulsion might get us to the outer edges of the solar system a little faster. It will not bridge the gap to another star. Fusion, antimatter, ion drives, all of them run into the same basic problems. Too slow, too heavy, too energy intensive, or some combination of all three. The tools that got us this far are not the tools that will take us the rest of the way. And so we are stuck. Not permanently, maybe, but for now. We can look at Alpha Centauri through telescopes. We can map its planets, analyze its light, study its behavior. We can imagine what it would be like to stand on a world orbiting those stars, to look up at a sky where the sun is just another faint point of light. We can imagine it in extraordinary detail, but we cannot go there, not yet. Not with anything we know how to build. The impossible dream of reaching the stars is still impossible for now. The physics is too hard, the distances too vast, the energy requirements too extreme. Every path forward is blocked by a problem we do not know how to solve. And some of those problems might not have solutions, but here is what keeps people working on this, despite the odds, despite the math, despite the walls. Humans have a long history of doing things that looked impossible right up until the moment we figured out how to do them. Heavier-than-air flight was impossible until it was not. Splitting the atom was impossible. Landing on the moon was impossible. Every one of those breakthroughs required not just better engineering, but a fundamental shift in how we thought about the problem. A willingness to abandon the tools that had gotten us so far and invent entirely new ones. Maybe interstellar travel is different. Maybe this time the universe really has said no in a way that no amount of cleverness can overcome. Or maybe somewhere in the equations we have not written yet, in the technologies we have not imagined, there is a way forward. A path that looks absurd today but will seem obvious in hindsight. The old ways will not work. We have established that. Chemical rockets are too slow. The rocket equation is too unforgiving. Relativity has drawn a line in the sand and told us we cannot cross it. Fine, understood, accepted. So, if the conventional path is closed, what is left? What happens when you take the problem of interstellar travel, strip away all the assumptions about how propulsion is supposed to work, and start over from scratch? What is left are ideas that sound insane until you run the numbers. Concepts that were dismissed as science fiction until physicists sat down with pencils and paper and realized they were not fiction at all, just very, very hard. Some of these ideas have been around for decades, quietly gathering dust in academic journals and declassified government reports. Others are so new that the ink on the equations is barely dry. None of them are easy, none of them are cheap, and none of them are guaranteed to work. But all of them share one thing in common. They take seriously the idea that if we are going to reach another star, we need to stop thinking like rocket engineers and start thinking like people who are willing to break things. Let us start with the oldest and in some ways the most straightforward of the radical ideas: nuclear pulse propulsion. The concept is simple in the way that a sledgehammer is simple. You take a nuclear bomb, you detonate it behind your spacecraft. The explosion pushes you forward. Repeat as necessary. This is not a joke. This is a real proposal that was studied in detail by actual scientists working for the United States government in the late 1950s and early 1960s. The project was called Orion, and for a brief window of time, it was considered the most plausible path to the outer solar system and possibly beyond. The basic idea came from physicist Stanislaw Ulam, one of the architects of the hydrogen bomb, and was developed further by Freeman Dyson, a theoretical physicist who spent much of his career thinking about the far future of humanity in space. Here is how it works. You build a large spacecraft with a thick steel plate at the back. The plate is called the pusher plate, and it is designed to absorb the force of nuclear explosions without vaporizing. Behind the spacecraft, you carry a supply of small nuclear bombs, not city-destroying warheads. Smaller devices, each one yielding maybe a kiloton or so of explosive force. You eject one bomb behind the ship, detonate it at a safe distance, and the expanding cloud of plasma from the explosion slams into the pusher plate. The plate transfers that momentum to the rest of the spacecraft through a system of heavy-duty shock absorbers. The ship accelerates. A few seconds later, you eject another bomb and do it again, and again, and again. Each explosion gives you a hard shove forward. String together enough explosions and you build up serious velocity. The numbers that came out of the Orion studies were remarkable. A well-designed nuclear pulse ship could theoretically reach speeds of 3 to 5% the speed of light. That would cut the travel time to Alpha Centauri down to somewhere between 80 and 140 years. Still longer than a human lifetime, but no longer an absurd multi-generational voyage stretching across millennia. You could launch a mission and reasonably expect that the grandchildren of the people who built it might live to see it arrive. The engineering challenges are significant but not insurmountable. You need a pusher plate that can survive repeated nuclear blasts without cracking or ablating away. You need shock absorbers capable of smoothing out accelerations that would otherwise crush the spacecraft and everything inside it. You need a way to store and eject nuclear devices reliably in the vacuum of space. And you need to do all of this while keeping the crew, if there is one, shielded from the radiation produced by hundreds or thousands of nuclear detonations happening just a few dozen meters behind them. But here is the thing, none of those problems are impossible. They are just hard. The materials exist, the physics is well understood. Freeman Dyson, who worked on Orion for years, believed until his death that the concept was not only feasible but could have been built with 1960s technology if there had been the political will to do it. He once said that if we had started construction on an Orion-class starship in 1965, it could have been on its way to Alpha Centauri by the mid-1980s. So why are we not riding nuclear bombs to the stars right now? 2 reasons. The first is the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear explosions in space. The treaty was signed at the height of the Cold War, and its primary goal was to limit the arms race and reduce radioactive fallout. But it had the side effect of killing Orion. You cannot build a spacecraft that works by detonating nuclear bombs if detonating nuclear bombs in space is illegal. The second reason is more visceral. People do not like the idea of launching nuclear weapons into orbit, even if the purpose is peaceful. The risk of an accident during launch, of a rocket carrying dozens or hundreds of nuclear devices exploding in the atmosphere and scattering radioactive material across half a continent, is enough to make most governments extremely nervous, and rightly so. One malfunction, one miscalculation, and you have turned a propulsion system into a catastrophe. Still, Orion remains on the table as a theoretical option. If we ever reach a point where the political and safety concerns can be addressed, the physics is there, the design is there. It is one of the few interstellar propulsion concepts that does not require inventing new physics or waiting for breakthroughs in materials science. It just requires a willingness to ride a controlled series of nuclear explosions across the solar system and hope nothing goes wrong. Let us move to something even more extreme: antimatter. Antimatter is the mirror image of normal matter. For every particle that exists, there is a corresponding antiparticle with the same mass but opposite charge. An electron has a negatively charged antiparticle called a positron. A proton has a negatively charged counterpart called an antiproton. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy. 100% of their combined mass converts directly into energy according to Einstein's equation. No other reaction in physics is that efficient. Not fusion, not fission, Nothing. The energy density of antimatter is staggering. A single gram of antimatter, if annihilated with a gram of normal matter, would release the energy equivalent of a 20-kiloton nuclear bomb. For comparison, the bomb dropped on Nagasaki in 1945 yielded about 21 kilotons, and it required several kilograms of plutonium to achieve that. 1 gram of antimatter contains the same punch as thousands of kilograms of chemical explosives or dozens of kilograms of enriched uranium. That is the kind of energy density you need if you want to accelerate a spacecraft to a meaningful fraction of light speed. In theory, an antimatter rocket works like this. You carry a small amount of antimatter in a magnetic containment vessel. Antimatter cannot touch normal matter, or it will annihilate instantly, so you have to levitate it using powerful magnetic fields. When you want thrust, you carefully feed tiny amounts of antimatter into a reaction chamber where it meets an equal amount of normal matter, typically hydrogen. The annihilation produces a burst of high-energy particles, mostly gamma rays and charged pions, which you direct out the back of the spacecraft using magnetic nozzles. The momentum of those particles pushes you forward. If you could carry even a few kilograms of antimatter, you could in principle accelerate a spacecraft to 10 or 20% the speed of light. That would get you to Alpha Centauri in 20 to 40 years, fast enough to make interstellar exploration conceivable within a human lifetime. Fast enough to matter. So why are we not building antimatter rockets? Because antimatter does not exist naturally in any usable quantity. The universe is overwhelmingly made of normal matter. Antimatter particles are occasionally produced in high-energy collisions, cosmic rays smashing into the upper atmosphere, particles decaying inside supernova remnants, but they annihilate almost immediately upon encountering normal matter. There are no antimatter asteroids to mine, no antimatter clouds to scoop up. If you want antimatter, you have to make it, and making it is absurdly difficult. The only way we know how to produce antimatter is by smashing particles together in accelerators at very high energies and occasionally, as a byproduct, generating antiparticles. CERN, the European Particle Physics Lab in Switzerland, produces antiprotons as part of its research. They have gotten very good at it. They can produce billions of antiprotons per hour. That sounds like a lot until you do the math. Billions of antiprotons weigh about 1 picogram. That is 1/1,000,000th of a gram. To produce a single gram of antimatter at current rates would take roughly 10 million years. Even if we could somehow scale up production by a factor of 1,000,000, which would require building accelerators vastly larger and more powerful than anything that currently exists, it would still take years to produce the kilograms of antimatter needed for a single interstellar mission. And the energy cost would be enormous. Current antimatter production is grotesquely inefficient. For every unit of energy you get out of antimatter annihilation, you have to put in billions of units of energy to produce the antimatter in the first place. You are not generating energy. You are storing it in the most expensive battery ever conceived. Then there is the storage problem. Antimatter cannot touch the walls of its container, or it will annihilate and release all its energy in a fraction of a second. That means you need magnetic confinement, but magnetic fields require power. If the power fails, even for an instant, the antimatter drifts into the walls and you have an explosion. A few grams of antimatter annihilating all at once would release more energy than most nuclear weapons. Storing kilograms of it on a spacecraft for decades is a problem that no one has solved. Antimatter propulsion is not impossible. The physics works, but the practical barriers are so enormous that it remains firmly in the realm of distant future speculation. We would need breakthroughs in particle physics, in energy generation, in magnetic containment, in materials science. We would need infrastructure on a scale that does not currently exist. And we would need a very good reason to invest the staggering resources required. Antimatter rockets are possible in the same way that building a pyramid on Mars is possible. Technically feasible, practically absurd, for now. There is another idea that sidesteps the fuel problem entirely by not carrying any fuel at all. Instead of pushing yourself forward with onboard propulsion, you let something else push you, specifically light. Light carries momentum, not much. A photon, the fundamental particle of light, has no mass, but it does have momentum proportional to its energy. When light hits an object, it exerts a tiny force. You do not notice this in daily life because the force is minuscule. But in space, where there is no friction and no air resistance, even a tiny continuous force can accelerate an object to high speeds given enough time. This is the principle behind solar sails, and it has been tested successfully on several spacecraft already. Japan's Icaros mission, launched in 2010, used a solar sail to travel through the inner solar system, propelled by nothing but sunlight reflecting off a thin reflective sheet. Solar sails work, but they are slow. Sunlight is diffuse, and it gets weaker the farther you get from the sun. By the time you reach the outer planets, there is not enough light pressure to provide meaningful acceleration. For interstellar travel, you need something much more powerful. You need a laser. This is the idea behind Breakthrough Starshot, a privately funded initiative announced in 2016 by billionaire investor Yuri Milner and physicist Stephen Hawking. The concept is beautifully simple. You build a ground-based or space-based array of extremely powerful lasers. You build a fleet of tiny spacecraft, each one weighing only a few grams and equipped with an ultra-thin reflective sail. You point the lasers at the sails and fire. The concentrated beam of light pushes the sail forward, accelerating it rapidly. Within minutes, the spacecraft reaches a significant fraction of the speed of light. You turn off the lasers. The spacecraft coasts the rest of the way to Alpha Centauri, arriving in about 20 years. The numbers are extraordinary. Starshot envisions craft weighing around 1 gram each, about the mass of a paperclip, attached to sails a few meters across. The laser array would deliver about 100 gigawatts of power, roughly the output of 100 nuclear power plants, focused into a tight beam and fired for just a few minutes. That brief pulse of energy would accelerate the craft to 20% the speed of light. At that speed, the journey to Alpha Centauri takes roughly 20 years. Add a few more years to send data back, and you could have images and measurements from another star system within a human lifetime. The challenges are formidable. Building a laser array powerful enough to deliver 100 gigawatts is possible but expensive. You would need thousands of individual lasers working in perfect coordination. The beam has to stay focused over millions of kilometers as the spacecraft accelerates. Any wobble, any misalignment, and the craft drifts out of the beam and loses thrust. The sail itself has to be incredibly thin, lightweight, and reflective. It has to survive the intense heat of the laser without warping or ablating. And the spacecraft, all 1 gram of it, has to carry cameras, sensors, a power source, a transmitter, and enough intelligence to orient itself and send data back across trillions of miles. There is also the problem of aiming. At 20% the speed of light, the spacecraft will cover the distance to Alpha Centauri in about 20 years, but it will not stop. It will scream past the star system at 60,000 kilometers per second, giving it only a few hours to gather data before it is gone forever. There is no fuel to slow down, no way to brake. It is a flyby mission, and you get one shot. Still, Starshot is one of the few interstellar concepts that does not require waiting for new physics. Lasers exist, light sails exist, miniaturized electronics exist. The engineering is hard, but it is not speculative, and the timeline is realistic. If funding were available, a test mission could launch within a few decades. That is faster than any other interstellar proposal currently on the table. Then there is fusion. Not the fusion that powers the sun, which is a chaotic mess of high-energy particles colliding in a superheated plasma, but controlled fusion. The kind you can start and stop, tune and direct, sustain inside a rocket engine. If we could master fusion propulsion, we would have access to energy densities far beyond anything chemical rockets can provide, with fuel that is relatively abundant and much easier to handle than antimatter. Fusion works by smashing light atomic nuclei together with enough force that they overcome their natural repulsion and merge into a heavier nucleus. The process releases energy because the combined nucleus weighs slightly less than the original pieces, and that missing mass gets converted into energy. The most promising fusion reaction for propulsion combines deuterium and tritium, both isotopes of hydrogen. Deuterium can be extracted from seawater. Tritium is rarer, but can be bred from lithium. A kilogram of fusion fuel contains millions of times more energy than a kilogram of chemical propellant. A fusion rocket could theoretically sustain thrust for months or years, accelerating continuously until it reached a significant fraction of light speed, then flipping around and decelerating on the other end. Travel time to Alpha Centauri could drop to a few decades, and unlike antimatter or laser sails, a fusion rocket would have the flexibility to stop, maneuver, explore. It would be a true starship, not just a one-way probe. The problem, and it is a big one, is that we do not know how to build a fusion reactor that works reliably, much less one compact and efficient enough to fit on a spacecraft. Fusion research has been ongoing since the 1950s. We have gotten very good at generating fusion reactions in the lab. We have even achieved net energy gain in a few experimental setups. But sustaining a controlled fusion reaction, extracting useful energy from it, and doing so in a package small enough and light enough to serve as a rocket engine remains an unsolved problem. The joke in the fusion community is that practical fusion power is always 30 years away and always has been. Still, progress is being made. Private companies and government labs are pursuing multiple approaches. Some use magnetic confinement, trapping the fusion plasma in powerful magnetic fields. Others use inertial confinement, compressing tiny fuel pellets with lasers until they ignite. A few are exploring entirely new concepts involving exotic field geometries and advanced materials. If any of these approaches succeeds, fusion propulsion moves from theoretical to feasible almost overnight. And then there are the ideas that live at the very edge of physics, concepts so speculative that even calling them theoretical feels generous. The most famous is the Alcubierre drive, named after physicist Miguel Alcubierre, who published a paper in 1994 describing a mathematical solution to Einstein's field equations that allows for faster-than-light travel without breaking relativity. The idea is not to move the spacecraft faster than light. That is still impossible. Instead, you manipulate space-time itself. You contract space in front of the ship and expand it behind, creating a bubble that carries the ship along with it. From the perspective of someone inside the bubble, the ship is not moving at all. It is space that is moving. The ship just goes along for the ride. And because there is no limit on how fast space itself can expand or contract, the ship can effectively travel faster than light without ever locally exceeding the speed limit. It is a brilliant piece of theoretical physics. It is also almost certainly not something we can actually build. The Alcubierre drive requires something called exotic matter, a hypothetical form of matter with negative energy density. Nothing we have ever observed or created has negative energy density. We do not know if exotic matter exists. We do not know how to make it. And the equations suggest you would need absurd quantities of it, possibly more mass energy than is contained in the observable universe, to create even a small warp bubble. Over the years, physicists have proposed modifications to the original concept that reduce the energy requirements. Some estimates bring the total down to something closer to the mass of Jupiter. Still absurdly impractical, but at least not larger than the universe. Other researchers have pointed out that even if you could build a warp drive, you might not be able to control it. Turning it on could create a runaway cascade of effects that would destroy the ship or sterilize the destination with lethal radiation. The Alcubierre drive is a beautiful idea. It shows that faster-than-light travel is not strictly forbidden by relativity. But showing that something is not forbidden is not the same as showing it is possible. And right now, the warp drive remains firmly in the category of things that work on paper and nowhere else. So where does that leave us? We have nuclear pulse propulsion, which could work but is politically and practically difficult. We have antimatter, which would work beautifully if we could produce and store it, which we cannot. We have laser sails, which are feasible and relatively near-term, but limited to tiny flyby probes. We have fusion, which would be transformative if we could crack the engineering, which we have not. And we have warp drives, which remain a fantasy until someone figures out how to make exotic matter or proves it does not exist. None of these are easy. All of them require breakthroughs. Some require technologies that do not exist yet. A few require rethinking the laws of physics, but they are the menu. These are the options if we want to cross 25 trillion miles in anything resembling a reasonable time frame. Chemical rockets will not do it. Conventional propulsion has hit its limit. If we are serious about reaching another star, we have to pick one of these paths and commit to solving the problems, no matter how hard they are. And assuming we solve them, assuming we build a ship capable of reaching a meaningful fraction of light speed, assuming we figure out how to generate the energy and survive the journey, we still have to deal with the people, or the machines, or whatever it is we plan to send, because the propulsion system is only part of the problem. The other part is making sure that whatever we send actually survives the trip. That is a different kind of nightmare, and it is where we are going next. Imagine this. You are 25 years old. You have just been selected for the most important mission in human history, a crewed flight to Alpha Centauri. The ship is ready. The fusion drive works. The life support systems have been tested. Everything checks out. You board with a crew of maybe a dozen others, all specialists, all brilliant, all carefully screened for psychological stability. The ship lifts off. You wave goodbye to Earth, watch the planet shrink behind you, and settle in for the journey. The destination is 4¼ light years away. Your ship will cruise at 10% the speed of light. That is fast, extraordinarily fast by any current measure. And it will still take 42 years to get there. 42 years, not 42 days, not 42 months, 42 years. You board the ship at 25. You arrive at Alpha Centauri at 67. If you arrive, if nothing breaks, if the ship holds together, if the crew holds together, if you hold together, let that sit for a second. 42 years inside a vehicle that cannot stop at a gas station, cannot pull over for repairs, cannot turn around if something goes wrong. 42 years breathing recycled air, drinking recycled water, eating food grown in hydroponic bays under artificial lights. 42 years staring at the same walls, walking the same corridors, seeing the same faces every single day. 42 years knowing that everyone you left behind on Earth is growing older without you, that your parents will likely die before you arrive, that your friends will move on, that the world you knew will change in ways you cannot predict or control. 42 years knowing that if something goes catastrophically wrong, there is no rescue, no backup, no plan B. You are on your own, in the most absolute sense those words have ever meant. This is the human factor, and it is every bit as hard as the propulsion problem, maybe harder, because we understand physics, we know how rockets work, we know the equations, but we do not fully understand what happens to a human mind when you lock it inside a metal tube for 4 decades and tell it there is no way out. We have some clues. Not great ones, but clues. We have studied astronauts on the International Space Station. They spend 6 months in orbit, sometimes a year. The station is cramped, about the size of a 6-bedroom house, shared by a rotating crew of 6 or 7 people. The environment is noisy, sterile, and monotonous. There is no weather, no seasons, no variety. The view out the window is spectacular, but after a few months, even that starts to feel repetitive. You have seen Earth from orbit. You have watched 1,000 sunrises. The novelty wears off. Astronauts report psychological strain, irritability, difficulty concentrating, disrupted sleep, a vague sense of disconnection from the people and places they left behind. Most of them handle it well because they are trained for it, because they know the mission is temporary, and because they can look down and see Earth spinning below them every 90 minutes. Home is right there, visible, close enough that if something went wrong, they could be back on the ground in a matter of hours. Now take that experience and stretch it across 42 years. Take away the view of Earth. Take away the knowledge that home is close. Take away the certainty that the mission will end. Because on an interstellar voyage, there is no quick return. There is no abort button. Once you leave, you are committed. The only way out is forward. The isolation would be crushing. Not just physical isolation, though that would be bad enough. Psychological isolation. You would be farther from other human beings than anyone in history. The distance between you and Earth would grow every second. At 10% the speed of light, you would cover about 18 million miles every day. After 1 year, you would be roughly 6.5 billion miles from home. That is farther than Pluto. After 5 years, you would be over 30 billion miles out. After 10 years, 65 billion miles. By the time you reached the halfway point, 21 years in, Earth would be more than 2 light years behind you. A radio signal sent from Earth would take over 2 years to reach you. Your reply would take another 2 years to get back. A simple conversation, a question and an answer would require a 4-year round trip. You could ask someone how they are doing and receive a response half a decade later telling you about a version of their life that no longer exists. At that distance, Earth would no longer look like a planet. It would look like a star. A faint blue dot lost among thousands of other dots, indistinguishable unless you knew exactly where to point your telescope. The sun would still be the brightest star in your sky, but only barely. It would not light your ship. It would not warm you. You would be alone in a way that no human being has ever been alone, and you would not be able to leave the ship. There is no shore leave on an interstellar voyage. No stops along the way, nothing to see outside except the slow creep of distant stars shifting position as you move through space. You would live your entire adult life inside a series of connected rooms, probably no larger than a small apartment building. Every day for 42 years, you would wake up in the same bed, eat in the same galley, work at the same stations, exercise in the same gym. You would see the same people, hear the same voices, smell the same recycled air. The ship would become your entire world, not metaphorically. Literally, there would be no world outside it. Just vacuum and radiation and emptiness stretching in every direction for trillions of miles. The psychological literature on long-duration confinement is not encouraging. Studies of people in isolated environments, Antarctic research stations, submarines, long-term solitary confinement show a consistent pattern. People adapt for a while, then they start to crack. Not everyone. Some people handle isolation better than others, but even the most psychologically resilient individuals report cognitive decline, emotional blunting, and a creeping sense of unreality after extended periods of isolation. The environment stops feeling real. Time stops feeling linear. The mind starts to drift. In the 1960s and 70s, researchers ran experiments where volunteers agreed to live in isolated, confined environments for months at a time. The results were mixed. Some participants did fine. Others developed depression, paranoia, and interpersonal conflicts that escalated into physical confrontations. And those experiments lasted weeks or months, not decades. Nobody has ever been confined for 42 years. We do not know what that does to a person because it has never been done. Then there is the social dimension. A crew of a dozen people might sound like enough for company. It is not. 12 people is a tiny community. Small enough that every personality clash, every disagreement, every minor annoyance becomes magnified. You cannot avoid someone you dislike. You cannot take a break from the group. You cannot leave. If 2 crew members develop a conflict, the rest of the crew has to live with it. If someone becomes depressed or unstable, there is no therapist to call, no hospital to check into. The crew has to manage it themselves. And they will have to manage everything themselves. Medical emergencies, equipment failures, interpersonal disputes. There is no mission control to call for advice, at least not in any useful sense. By the time you are a few years into the mission, the communication delay is measured in years. You cannot radio Earth and ask for help. You have to solve every problem on your own, immediately, with whatever resources and expertise you have on board. History is full of examples of small, isolated groups turning on each other, mutinies, murders, social collapse. The Franklin expedition to the Arctic in the 1840s ended with the entire crew dead, some of them having resorted to cannibalism. The Donner Party, trapped in the Sierra Nevada mountains during the winter of 1846, descended into similar horror. These were not weak people or poorly planned expeditions. They were experienced, well-supplied, and motivated. But isolation, starvation, and desperation broke them. An interstellar crew would not face starvation, assuming the life support systems work, but they would face something arguably worse, the knowledge that there is no rescue, no escape, no end in sight except the one 4 decades away. And if something goes wrong, if the ship breaks down, if the crew fractures, there is nothing anyone on Earth can do about it. The mission would just end, the ship would drift, the crew would die, and Earth would not know for years. Some mission planners have proposed psychological interventions to mitigate these risks. Careful crew selection, ongoing mental health monitoring, structured routines to provide a sense of normalcy, virtual reality environments to simulate being outdoors or in different locations, regular communication with Earth, even if the delays make real conversation impossible. All of these might help, but none of them solve the fundamental problem. You are still locked in a can. You are still isolated. You are still decades away from anywhere that matters. And no amount of clever planning can change that. Then there is the question of leadership. Who is in charge on a 42-year mission? Do you have a single captain who holds authority for the entire voyage? What happens if that person dies or becomes incapacitated? Do you elect a new leader? What if the crew disagrees? What if factions form? A ship is not a democracy. It cannot be. Decisions have to be made quickly, especially in emergencies. But authoritarianism in a confined space breeds resentment. And resentment over 42 years can build into something dangerous. You could rotate leadership. Different people take command for different phases of the mission, but that creates its own problems. Consistency matters. Trust matters. If the crew does not believe in the leadership, if they start second-guessing decisions or undermining authority, the mission is in trouble, and there is no HR department to mediate, no court system, no external authority to appeal to. Whatever social structure the crew builds, they have to maintain it themselves for 4 decades. One mistake, one breakdown in trust, and the whole thing could collapse. And we have not even talked about the biology. 42 years in microgravity or artificial gravity, depending on how the ship is designed, would wreak havoc on the human body. Bone density loss, muscle atrophy, cardiovascular deconditioning, vision problems caused by fluid shifts in the skull, increased cancer risk from cosmic radiation. Even with exercise and medical interventions, the crew would arrive at Alpha Centauri significantly weaker than when they left. Some of them might not arrive at all. People die, even healthy people. Heart attacks, strokes, accidents. Over a 42-year span, statistically, you would expect at least 1 or 2 deaths in a crew of 12. And when someone dies on an interstellar mission, you cannot bring the body home. You cannot have a funeral with family. You bury them in space, or store them in a freezer, or, more likely, recycle their remains to recover water and nutrients for the life support system. That is the reality. It is grim, but it is efficient, and efficiency matters when you are that far from resupply. Some mission concepts sidestep the human factor problem by not sending humans at all. Send robots, send AI, send tiny probes like Breakthrough Starshot that do not need life support or psychological counseling. Let the machines make the journey and beam the data back. That is probably the smart approach. Machines do not get lonely. They do not fight. They do not care that the mission takes 42 years. You could send 1,000 of them and not worry if a few fail. But there is something deeply unsatisfying about that. Sending a robot to another star is not the same as going there. It is scouting. It is reconnaissance. It is gathering data. But it is not exploration in the way humans understand that word. Exploration means standing on new ground, breathing new air, if there is any, looking up at an alien sky, planting a flag, leaving footprints, making the place human, even if only for a moment. You cannot do that with a probe. A probe collects information. A human experiences it. And experience is what makes exploration meaningful. So if we want to send people, if we want humans to walk on a planet orbiting Alpha Centauri, we have to accept that 42 years is probably the best-case scenario. And even that assumes we can build a ship capable of 10% light speed, which we cannot, not yet. More realistic estimates, using propulsion systems that might be feasible within the next century, put the travel time closer to 100 years, or longer. At that point, you are not sending a crew, you are sending a society, a generation ship. The people who launch the mission are not the people who arrive. They live their lives on the ship, have children, raise them, grow old and die. Their children do the same, and their children. And maybe their children. Depending on how long the journey takes, you might need 3 or 4 generations before anyone sets foot on the destination. Generation ships are a staple of science fiction, and for good reason. They are one of the few ways to make interstellar travel work with anything resembling current or near-future technology. But they raise questions that make the 42-year crewed mission look simple. How do you maintain social cohesion across generations? How do you prevent the later generations from deciding they do not care about the mission and just want to turn around or stop somewhere else? How do you preserve knowledge and technical skills when the original crew, the people who built and understood the ship, are long dead? How do you keep a tiny population genetically healthy over that many generations? Genetic drift is a real problem. If you start with a population of a few hundred people, which is about the minimum you would need to maintain genetic diversity, you are already in trouble. Small populations lose genetic variation quickly. Recessive traits start to appear. Inbreeding becomes a risk. You would need careful genetic management, possibly involving frozen embryos or genetic engineering, to keep the population viable. And you would need to enforce it, which means someone has to have the authority to decide who reproduces with whom. That is eugenics. And it is unavoidable on a generation ship. Then there is the question of purpose. The first generation boards the ship, knowing they are sacrificing their lives for a mission that will benefit their descendants. Fine, that is heroic. But what about the second generation? They did not choose to be born on a ship. They did not volunteer for the mission. They are just there, stuck, living out their lives in a metal tube because their parents decided to go to Alpha Centauri. Do they resent that? Do they rebel? Do they teach their children to value the mission, or do they teach them that the whole thing was a mistake? Over multiple generations, the culture on the ship would drift, language would change, traditions would evolve, the connection to Earth would fade. Eventually, the ship becomes its own world, and the idea of reaching Alpha Centauri becomes a myth, something the elders talk about, but no one really believes. The mission fails not because the ship breaks down, but because the people on it stop caring. This is not speculation. This is what happens to isolated human populations over time. They diverge, they forget. They reinterpret their own history. A generation ship would need extraordinarily strong cultural and institutional frameworks to prevent that. And even then, it might not be enough. James Eubanks, a mission design expert, has said that he thinks we will reach Alpha Centauri with small probes, probably launching in the 2040s and arriving in the 2060s. But crewed missions, he said, will be a task for the next century. That is optimistic phrasing, for we do not know how to do it yet. The technology is not there, the biology is not there, and the psychology, the understanding of what it takes to keep humans sane and functional over interstellar timescales, is not there either. So we are left with a choice: send machines and accept that the journey will be impersonal, or send people and accept that the cost, the human cost, might be higher than we are willing to pay. 42 years in a steel can is not just a logistics problem. It is a test of everything that makes us human. Our ability to endure, to cooperate, to find meaning in isolation, to hold on to hope when home is a point of light 2 light years behind you and the destination is still 2 light years ahead. And even if we solve all of that, even if we build the perfect ship and select the perfect crew and manage the psychology and the biology and the social dynamics, we still have to get them there alive, because space is not empty, It is full of things that want to kill you. Radiation, micrometeorites, the cold, the void. The ship is not just a home for 42 years, it is a lifeboat. And the ocean it is crossing is more hostile than anything on Earth. That is the next problem, and it is waiting for us. Here is something most people do not think about when they imagine space travel. Space is not a vacuum in the way an empty room is empty. It is not just the absence of air, it is an environment. An active, hostile environment that is constantly trying to destroy anything solid enough to exist inside it. And the farther you get from Earth, the worse it gets. Because Earth, for all its problems, sits inside a protective bubble, the magnetosphere, a vast magnetic field generated by the churning of molten iron in the planet's core. That field deflects most of the charged particles streaming out from the sun and sweeping in from the galaxy beyond. It is why you can walk outside without your DNA getting shredded. It is why life exists here at all. Step outside that bubble, leave the magnetosphere behind, and you are exposed, naked, standing in the crossfire of radiation that has been killing things since the universe began. Cosmic radiation comes in two main flavors. The first is solar radiation. Charged particles, mostly protons and electrons, constantly streaming out from the sun in what scientists call the solar wind. The sun does not shine quietly. It churns and boils and throws tantrums. Solar flares erupt from its surface, blasting waves of high-energy particles into space. Coronal mass ejections hurl billions of tons of plasma outward at millions of miles per hour. If one of those events catches you in open space without shielding, you are in serious trouble. The radiation dose from a large solar flare can be lethal within hours. Not theoretically lethal, actually lethal. Your cells start dying, your bone marrow shuts down, your intestines liquefy. You do not get cancer someday. You die within days or weeks from acute radiation poisoning. Astronauts on the International Space Station are partially protected because they are still close to Earth, still inside the outer edges of the magnetosphere. But even they have to take cover during solar storms. The station has shielded areas where the crew can huddle and wait out the worst of it. On an interstellar mission, there is no magnetosphere, no planetary shield, just you and the ship and whatever shielding you manage to bring along. And solar radiation, as dangerous as it is the easier problem to manage, because the sun is predictable. We can monitor it, we can see flares coming, we can warn the crew and give them time to take shelter. The second flavor of cosmic radiation is worse. Galactic cosmic rays. These are high-energy particles, mostly protons, but also heavier nuclei like carbon, oxygen, and iron, traveling at close to the speed of light. They come from outside the solar system, from supernova remnants, from pulsars, from the violent deaths of massive stars scattered across the galaxy. They have been accelerated to such extreme energies that when they hit something, they do not just damage it, they punch straight through. A galactic cosmic ray does not care about your ship's hull. It does not care about your spacesuit. It passes through metal, through plastic, through water, through your body, like a bullet through fog. And as it goes, it tears apart everything it touches at the molecular level. The human body is not built to handle this. Your cells contain DNA, long fragile molecules that encode the instructions for building and running you. Cosmic rays shred DNA. They break the strands. They scramble the sequences. Most of the time, your cells can repair the damage. They have mechanisms for that. But repair is not perfect. Mistakes accumulate. Some of those mistakes turn into cancer. Some cause cells to die outright. Some damage the stem cells in your bone marrow or your intestines, the cells responsible for making new blood or lining your gut. Lose too many of those, and your body stops being able to maintain itself. You get sick, you develop anemia, you become vulnerable to infections, your organs start to fail. NASA has run the numbers on this. A crewed mission to Mars, which would take about 6 to 9 months each way, would expose astronauts to radiation doses roughly equivalent to getting a full-body CT scan every 5 or 6 days for the entire trip. That is manageable. Unpleasant, but manageable. The increased lifetime cancer risk is somewhere between 1 and 5%, depending on age, sex, and genetic factors. Astronauts accept that risk because the mission is short and the science is important. Now scale that up to an interstellar mission, 42 years in deep space, 42 years of continuous exposure to galactic cosmic rays with no planetary magnetosphere to hide behind. The cumulative dose would be orders of magnitude higher, and we are not talking about a slightly elevated cancer risk. We are talking about near certainty. Every crew member would develop cancer, probably multiple cancers. Some would die from it before reaching Alpha Centauri. The rest would arrive sick, weakened, their immune systems compromised, their bodies breaking down at the cellular level. And it gets worse. Cosmic rays do not just cause cancer, they cause acute damage to the central nervous system. Studies on mice exposed to high-energy particles, the kind you get in deep space, show cognitive decline, memory problems, difficulty learning new tasks, increased anxiety, changes in personality. The particles damage neurons directly and trigger inflammatory responses that degrade brain tissue over time. Astronauts on a multi-decade interstellar voyage would not just be fighting cancer, they would be fighting dementia. By the time they arrived, some of them might not remember why they came. Then there is Proxima Centauri itself, the destination, the nearest star, and it is not a friendly place. Proxima is a red dwarf, smaller and cooler than the Sun, but it is also far more active. Red dwarfs are known for throwing massive stellar flares, sudden eruptions of radiation, and charged particles that make solar flares look tame. NASA has studied Proxima's flaring behavior in detail. A planet sitting in the habitable zone around Proxima, close enough that liquid water could exist on its surface, would be bathed in X-ray radiation, on an average day about 500 times what Earth receives. During a large flare, which happens regularly, the X-ray dose jumps to 50,000 times Earth's levels. 50,000 times. If you were in orbit around Proxima Centauri when one of those flares hit, it would not matter how good your shielding was. The radiation dose would be catastrophic. You would have minutes to get behind something thick and dense, or you would be dead before the flare subsided. And even if you survived, the electronics on your ship probably would not. High-energy radiation does not just hurt people, it fries circuits, it corrupts data, it degrades materials. Everything from computer processors to solar panels to structural composites breaks down faster under intense radiation. A ship that survives the 42-year journey through interstellar space could arrive at Proxima Centauri only to be crippled by the star it came to explore. So the radiation problem is not optional. It is not something you can ignore or hand-wave. If you are sending people to another star, you need shielding, real physical shielding, and that is where the engineering nightmare begins. Because shielding against cosmic rays is hard, really hard. Most people assume shielding works like armor. You put a thick wall between yourself and the radiation, and the wall stops it. That works for low-energy particles. It works for solar wind. You can block that with a few centimeters of aluminium or plastic. But galactic cosmic rays are different. They are moving so fast and carrying so much energy that when they hit a solid barrier, they do not just stop. They interact with the atoms in the barrier and create secondary particles. Sometimes those secondary particles are even more dangerous than the original cosmic ray. Heavy shielding can actually make the problem worse. This is called secondary radiation, and it is why you cannot just wrap your spacecraft in a giant block of lead and call it a day. The best shielding materials are light elements. Hydrogen, helium, carbon. They produce fewer secondary particles when hit by cosmic rays. Water is particularly good because it is dense, readily available, and made of hydrogen and oxygen. Some spacecraft designs propose surrounding the crew compartment with tanks of water, using the water as both a radiation shield and a consumable resource. That works in principle. In practice, it means carrying hundreds or thousands of tons of water, and water is heavy. Every kilogram of shielding is a kilogram you have to accelerate, coast with for 42 years, and then decelerate at the other end. The rocket equation rears its head again. The more shielding you carry, the more fuel you need. The more fuel you need, the heavier the ship. The heavier the ship, the more fuel. It spirals quickly. Some estimates suggest that to reduce the radiation dose on an interstellar mission to levels comparable to what astronauts experience on the space station, you would need shielding massing several meters thick in every direction. That is not a spacecraft anymore. That is a fortress. And fortresses do not accelerate to 10% the speed of light. There have been proposals for active shielding. Instead of using mass to block particles, you generate a magnetic field around the spacecraft, a miniature magnetosphere that deflects charged particles the way Earth's magnetic field does. It is an elegant idea. A strong enough magnetic field could protect the crew without adding much mass. The problem is generating that field. You need powerful superconducting magnets running continuously for decades. That requires energy, a lot of it, and it requires the magnets to not fail, ever. If the field drops, even for a few hours, the crew is exposed, and superconducting magnets are finicky. They have to be kept extremely cold. They do not like vibration. They do not like getting hit by cosmic rays themselves, which can cause quenches where the superconductor suddenly stops superconducting and the whole system shuts down. Building a magnetic shield that can run reliably for 42 years in deep space is a problem no one has solved yet. And then there are the micrometeorites. Space, despite being mostly empty, is not completely empty. There is dust. Tiny grains of rock and ice left over from the formation of the solar system, or chipped off asteroids and comets by collisions. Most of these grains are microscopic. A few are the size of sand. Occasionally, you get something the size of a pebble. On Earth, they burn up in the atmosphere. In space, they just keep drifting. The solar system is full of them. At normal spacecraft velocities, a few kilometers per second, micrometeorites are a nuisance. They pit your hull, they scratch your windows, they can damage delicate instruments, but they are not catastrophic. The International Space Station gets hit by tiny particles all the time. The impacts leave little craters, but the station's hull is thick enough that nothing gets through. Space shuttle windows came back from orbit, covered in tiny chips from micrometeorite strikes. Annoying but survivable. Now imagine moving at 10% the speed of light. That is 30,000 kilometers per second. At that speed, kinetic energy scales as the square of velocity. A grain of sand, something weighing a fraction of a gram, hitting your ship at 30,000 kilometers per second, carries as much energy as several kilograms of TNT. A pebble, something you could hold in your hand, hits with the force of a nuclear bomb. Not an exaggeration, actual nuclear bomb levels of energy. The impact would vaporize anything it touched. It would punch through your hull, through your shielding, through your ship, out the other side, leaving a glowing tunnel of destruction in its wake. And you cannot see them coming. Micrometeorites do not show up on radar. They are too small. They do not reflect enough light to spot with telescopes unless you are looking right at them, and they are very close, at which point it is too late. A grain of sand coming at you at 30,000 kilometers per second gives you no warning. It is just there, and then it is through your ship, and everything in its path is gone. Detecting and avoiding micrometeorites at interstellar velocities is one of the great unsolved problems of starship design. You could try to map the debris field ahead of you, identify regions with higher concentrations of dust, and steer around them, but space is big. Dust clouds are sparse. You might avoid the obvious hazards and still get unlucky. One random grain in the wrong place at the wrong time, and the mission is over. The ship is crippled or destroyed, the crew is dead, and no one on Earth will know for years because the light carrying the news of your death is still crawling back across 4 light-years of space. Some designs propose shielding against micrometeorites using a Whipple shield, a concept developed in the 1940s by astronomer Fred Whipple. The idea is simple. You put a thin sheet of material some distance in front of your main hull. When a micrometeorite hits the sheet, it vaporizes on impact, turning into a cloud of expanding plasma. The plasma spreads out as it travels the gap between the shield and the hull, and by the time it reaches the hull, the energy is distributed over a much larger area. The impact is no longer catastrophic. It is survivable. Whipple shields work. The International Space Station uses them. The problem is that they are designed for low-velocity impacts. At interstellar speeds, the energies are so high that even a Whipple shield might not be enough. You would need multiple layers, thick layers, spaced far apart, and again, every layer adds mass, and mass is the enemy. You could build a ship tough enough to survive micrometeorite impacts at 0.1c, but it would be so heavy that accelerating it to 0.1c in the first place would require more energy than we know how to generate. There is another approach. Do not armor the ship. Make it expendable, or at least part of it. Some proposals suggest sending not one large spacecraft, but a fleet of small ones. Thousands of tiny probes, each one carrying a fraction of the mission's instruments and data storage. They travel together in a loose formation. Some get hit by micrometeorites and are destroyed. The rest keep going. It is a numbers game. You accept that you are going to lose some, maybe most. As long as a few make it through, the mission succeeds. That works for unmanned probes. It does not work for people. You cannot send 1,000 crewed ships and accept that 990 of them will be destroyed en route. The math does not care, but ethics does. And beyond the radiation and the micrometeorites, there is the void itself, the vacuum. People think of vacuum as nothing, but vacuum is an active environment. Materials behave strangely in vacuum. Plastics and rubbers outgas. They release trapped gases slowly over time, degrading and becoming brittle. Metals cold weld. If 2 clean metal surfaces touch in vacuum, the atoms at the surface can bond directly to each other because there is no oxide layer or contaminant film to keep them apart. Moving parts seize. Lubricants evaporate, seals fail. Spacecraft designers know this. They use special materials, special coatings, special lubricants designed to survive in vacuum. But those materials are tested for missions lasting months or years, not decades, not 42 years. No one knows what happens to a spacecraft after 42 years in hard vacuum. We have never built anything that lasted that long in space. Voyager has been out there for almost 50 years, but Voyager is not a life support system. It is a flying antenna with some instruments bolted on. It does not have moving parts that need to keep moving. It does not have seals that need to stay sealed. And even Voyager is failing. Its instruments are shutting down one by one as systems degrade and power dwindles. A crude interstellar ship would be far more complex. Life support systems, air recyclers, water purifiers, food production, power generation, computers, communication systems, propulsion, navigation, all of it running continuously for decades with no opportunity for resupply or major repairs. Every component has a lifespan. Every seal will eventually leak. Every circuit will eventually fail. Redundancy helps. You build backups. Backups for the backups. You carry spare parts. You train the crew to repair and fabricate replacements. But there is a limit. You cannot carry spares for everything. You cannot anticipate every failure mode. At some point, something critical will break, and the crew will have to improvise or die. The cold does not help. Space is not uniformly cold. Near a star, you can actually get quite hot because there is no atmosphere to carry heat away. You heat up from radiation and have to actively cool yourself. But in interstellar space, far from any star, you are surrounded by the cosmic microwave background, the leftover radiation from the Big Bang. It has a temperature of about 2.7 degrees above absolute zero. That is cold, unimaginably cold. Everything wants to freeze. Your ship has to generate its own heat, maintain its own temperature for the entire journey. Any failure in the heating system, any leak in the insulation, and the temperature drops. Water freezes, fluids thicken, electronics stop working, people die. And then there is thermal cycling. As the ship rotates or maneuvers, different parts are exposed to sunlight or starlight or shadow. Materials expand when heated and contract when cooled. Do that enough times and they crack. Welds fail, joints loosen. Structures that were sound at launch develop stress fractures after years of thermal cycling. You can design for it. You can choose materials that handle temperature changes well. But you cannot eliminate the problem. And over 42 years, even small cracks propagate. Small problems become big problems. Big problems become catastrophic failures. This is the cosmic gauntlet. Radiation that shreds your DNA, micrometeorites that hit like bombs, vacuum that degrades your materials, cold that wants to freeze you, heat that wants to cook you. Thermal cycling that cracks your structure, and all of it happening simultaneously, relentlessly, for 42 years straight, with no pause, no shelter, no rescue. The ship is not just a vehicle, it is a lifeboat adrift in the most hostile ocean imaginable. And every single system on board, every seal, every wire, every rivet has to work perfectly for 4 decades or everyone dies. People hear the phrase 25 trillion miles and think the distance is the problem. The distance is a problem, but the environment is worse because distance is passive. It just sits there. The environment is active. It is trying to kill you every second of every day, and it does not get tired. It does not take breaks. Radiation does not stop because you have had a hard week. Micrometeorites do not avoid you because you are having a bad day. The void does not care about your mission or your dreams or the fact that you have come farther than any human in history. It is indifferent, perfectly, absolutely indifferent. And indifference at cosmic scales is more dangerous than any malice. So if you are going to send people to Alpha Centauri, you do not just need a fast ship. You need a ship that can survive, that can protect its crew from an environment that wants to kill them in a dozen different ways simultaneously. You need shielding that works without adding so much mass that the ship cannot move. You need systems that run for decades without failing. You need a hull that can take hits from micrometeorites without disintegrating. You need redundancy built on redundancy, backups stacked so deep that even when half your systems fail, the ship keeps going. And even then, you are betting everything on the hope that nothing unexpected happens, that there are no design flaws you missed, no failure modes you did not anticipate, no bad luck. And the worst part is that you are betting with lives. The crew cannot turn around. They cannot call for help. If something goes catastrophically wrong, there is no rescue mission, no backup plan. They are 4 light years from home in a ship that is falling apart, surrounded by a universe that does not care whether they live or die. The only thing standing between them and oblivion is the hull. A few meters of metal and plastic and composite materials separating them from hard vacuum and cosmic radiation and the endless cold. That hull has to hold. The systems have to work. The ship has to survive, because if it does not, everyone on board becomes part of the void. Just more debris drifting through interstellar space, frozen, silent, forgotten. That is what the cosmic gauntlet costs. That is the price of crossing 25 trillion miles, not just the decades, not just the isolation, the constant, grinding, relentless assault of an environment that has killed everything it has ever touched. And there is no way around it. You cannot negotiate with radiation. You cannot dodge micrometeorites you cannot see. You cannot wish away the vacuum or the cold or the slow degradation of every system on your ship. You can only prepare as best you can, launch, and hope you are smart enough and lucky enough to make it through. And even if you do make it through, even if the ship survives the journey and the crew arrives alive at Alpha Centauri, they still have to deal with the fact that they are now 25 trillion miles from home, 4 light years away. Far enough that a radio signal sent from Earth takes over 4 years to reach them. Far enough that a message sent back takes another 4 years to return. Far enough that any conversation, any exchange of information, any request for help requires 8 years round trip. By the time you ask a question and get an answer, everything has changed. Earth has moved on. The people you knew are older. Some are dead. The world you left behind is not the world that answers, and you are alone. Truly, deeply alone. In a way no one has ever been before. That is the next wall, the silence, and it is waiting. Communication delay is not something most people think about when they imagine interstellar travel. They picture spaceships talking to mission control the way astronauts on the International Space Station do. Real-time conversation. Questions answered immediately. Problems solved with input from experts on the ground. That works fine when you are in low Earth orbit, a few hundred kilometers up. The radio signal takes a fraction of a second to travel that distance. You can have an actual conversation, pause, response, back and forth. It feels normal. The moon is farther, about 240,000 miles. Light takes roughly 1¼ seconds to cover that distance. So when astronauts on the Apollo missions talked to mission control, there was a delay. You would hear them speak, wait 2½ seconds for the round trip, then hear the response. Noticeable but manageable, still close enough that it felt like communication. Mars, depending on where it is in its orbit relative to Earth, sits anywhere from about 34 million miles to 250 million miles away. At the closest approach, light takes roughly 3 minutes to get there. At the farthest, about 22 minutes. A conversation with someone on Mars would involve asking a question, waiting 6 to 44 minutes for a reply, depending on orbital positions. You could not have a back-and-forth discussion. You would send a message, go do something else, come back later, and check if they had responded. It would feel more like email than conversation, annoying but workable. Alpha Centauri is not 3 light-minutes away. It is not 20 light-minutes away. It is 4.24 light-years away. That is the distance to Proxima Centauri, the nearest of the 3 stars in the system. Alpha Centauri A and B, the larger binary pair, sit slightly farther, roughly 4.37 light-years depending on how you measure. Either way, the communication delay is the same order of magnitude, 4¼ years, one way, 4 years, 3 months, and some change. That is how long it takes for a radio signal, traveling at the speed of light, the absolute fastest anything can move according to the laws of physics, to cross the gap between Earth and Alpha Centauri. You send a message from your ship. It propagates outward as an expanding sphere of electromagnetic radiation, spreading through the void at 186,000 miles per second. It crosses the orbit of Pluto in a few hours. It exits the solar system. It keeps going for 4 years and 3 months. The people who sent that message age. The world changes. Governments rise and fall. Babies are born and start walking and talking and going to school. And the message is still in transit, still crawling across the interstellar gulf. Not because it is slow. Nothing in the universe is faster. But because the distance is so absurdly, incomprehensibly large that even light takes years to cross it. When the message finally reaches Earth, assuming anyone is still listening, they receive it. They process it. They compose a reply. Maybe it is an answer to a question. Maybe it is news from home. Maybe it is instructions for dealing with some problem the crew reported. Whatever it is, they send it back, and that reply takes another 4 years and 3 months to return. By the time the crew receives the response, 8½ years have passed since they sent the original message. 8½ years. An entire elementary school education. A full 2-term presidency. Longer than World War II lasted. Try to imagine what that does to the concept of communication. You cannot ask for help and expect a timely answer. You cannot report a problem and wait for mission control to tell you how to fix it. By the time they respond, the problem has either been solved or it has killed you. There is no middle ground. You are on your own in the most absolute sense those words have ever carried. Every decision, every repair, every crisis has to be handled by the people on the ship with the knowledge and resources they brought with them. If something breaks and no one on board knows how to fix it, it stays broken. If someone gets sick and the onboard medical equipment cannot treat it, they die. If a critical system fails and the spare parts you carried are not the right ones, the mission is over. Mission control, in any practical sense, stops existing. They can send updates, they can provide information, they can offer suggestions based on whatever the crew reported years ago. But they cannot guide, they cannot manage, they cannot intervene. The crew is not taking orders from Earth. Earth is too far away to give orders. The crew is making every decision themselves, knowing that by the time Earth hears about it, it will be ancient history. And it is not just operational decisions, it is personal communication too. Imagine you are on that ship. You left Earth at 25. You have a family, parents, siblings, friends, maybe a partner who stayed behind. You want to stay in touch. So you send messages, you record videos, you talk about what life is like on the ship, what you are seeing, how you are feeling. You ask how everyone is doing. You send your love. You hit transmit. The message begins its 4-year journey. 4 years later, your message arrives. Your parents, if they are still alive, see your face, hear your voice. You look exactly as you did 4 years ago, because that is when the message was sent. They record a response. They tell you what has been happening, who got married, who had kids, who died. They tell you they miss you. They send it back. Another 4 years. You receive their reply 8 years after you sent the original message. You are now 33 years old. The person talking to you in the video is your parent from 4 years ago. If they recorded the message at 70, they are 74 now, assuming they are still alive. And you will not know if they are alive until their next message arrives, which will be years from now. If they died last year, you will not find out until 3 years from now, when the message carrying that news finally reaches you. You could spend years sending messages to someone who is already dead, and you would not know. Every conversation is out of sync. You talk to ghosts, echoes of people who existed years ago. The person you are speaking to is not the person who will hear you. The person responding to you is not the person you were when you sent the message. You are communicating across time as much as across space. And the gap keeps widening. Every year you spend on the ship is another year Earth moves on without you. The world you left will not be the world you return to, if you return at all. It will be older, different. The people will be different. The culture will have shifted. Technology will have advanced or collapsed. Wars might have started. Plagues might have swept through. You will not know. You will get news, but it will always be years out of date, stale, historical, irrelevant to your present, because by the time you hear it, it is your past. This is the cost of distance, not just physical separation, but temporal separation. The speed of light is finite. Information cannot travel faster, and when the distances are measured in light years, information takes years to move. That creates a gap that no amount of technology can close. You can build better transmitters, better receivers, better computers to encode and decode the signals, but you cannot make the signal travel faster than light. Relativity does not allow it. The gap is permanent, absolute, unbridgeable. Some mission planners have suggested that crews should accept this from the start. That psychological preparation for communication delays is part of the training. You go in knowing that Earth is not going to be there for you in any real-time sense, that you are a separate entity, a colony, a seed. You carry Earth with you in your culture, your knowledge, your genetics, but you are no longer part of Earth in any operational sense. You are independent, not by choice, but by necessity. The physics gives you no other option. That independence is both liberating and terrifying. Liberating because the crew is free to make their own decisions without waiting for approval from a distant authority. They can adapt, improvise, take risks, and change plans as needed without filing reports and waiting years for permission. The mission is theirs. They run it. They own it. Terrifying because there is no safety net, no backup, no one to call when things go wrong. The ship is a lifeboat adrift in the cosmic ocean, and the crew is the only thing standing between survival and oblivion. This is what people mean when they talk about the point of no return. It is not a specific location in space. It is a threshold. The moment when Earth stops being able to help you in any meaningful way. For a mission to Mars, that threshold is crossed fairly early, but it is temporary. Mars is close enough that communication delays are measured in minutes, not years. You are on your own for the duration of the mission, but the mission is short, a few years at most. And rescue, while difficult, is at least theoretically possible. Another ship could be sent. It would take time, but it could be done. For a mission to Alpha Centauri, the point of no return is crossed the moment you leave Earth orbit. From that point on, you are beyond rescue. If the ship breaks down a year into the journey, Earth will not know for 4 years. By the time they receive the distress signal, you have been dead for years. If they decided to send a rescue mission, which they would not because the cost would be prohibitive and the odds of success nearly zero, it would take decades to reach you, and by then there would be nothing left to rescue. The mission is no rescue, no resupply, no return. Not as a tagline, as a fact. You cannot be rescued because the distances are too vast. You cannot be resupplied because there is nothing out there to supply you with. And you cannot return because the energy cost of turning around and decelerating and accelerating back toward Earth is prohibitive. The ship is built to go one way, forward, to the destination. Everything is committed to that. Fuel, trajectory, time. Once you launch, the decision is locked in. You are going to Alpha Centauri, or you are dying along the way. Those are the only two outcomes. That finality changes the psychology of the mission in ways that are hard to articulate. Astronauts on the space station know they can come home. Astronauts on a Mars mission know they can come home. The journey might be dangerous, the mission might fail, but the option to return exists. For an interstellar crew, that option does not exist. Home is not a place they can go back to. It is a place that used to exist 4 years in the past. By the time they arrive at Alpha Centauri, Earth will be decades older. The Earth they left will be gone, not destroyed, just different, changed, aged. The people they knew will be elderly or dead. The children they left behind will be adults. The world will have moved on, and if they spend 42 years traveling to Alpha Centauri, then another 42 years traveling back, assuming they even attempt the return journey, they will arrive at an Earth that is 84 years older than the one they left. Everyone they knew will be dead. The political systems, the economic systems, the cultural touchstones, all of it will have shifted. They will be strangers in their own world. Time travelers, not by moving through time, but by moving through space so slowly that time outran them. Some theorists have pointed out that relativistic time dilation could reduce the subjective experience of the journey for the crew. If the ship were traveling at a significant fraction of the speed of light, say 70 or 80%, time would pass more slowly on the ship relative to Earth. The crew might experience the journey as lasting 20 or 30 years, while Earth ages by 50 or 60. But that only makes the problem worse. You come home younger than you should be. Everyone you knew is even older or longer dead. The gap widens. You are not just separated by distance, you are separated by time, and time, unlike distance, only moves in one direction. The philosophical weight of this is staggering. The crew of an interstellar mission is not just leaving Earth, they are leaving the present. They are stepping out of the timeline of human civilization and into their own private timeline, one that runs parallel but does not sync up. Every message they send is a message to the past. Every message they receive is a message from the past. They exist in a permanent state of delay, never quite in sync with the rest of humanity, always a few years behind or a few years ahead, depending on how you count. Some people hear this and think it sounds lonely. It is worse than lonely. Loneliness implies the possibility of reconnection. You can be lonely and then not lonely when someone shows up. But the crew of an interstellar ship cannot reconnect, not in any real sense. They can send messages, they can receive messages, but they cannot have a conversation, they cannot share a moment. They cannot experience anything simultaneously with the people they left behind. The connection is severed, not by choice, but by physics. And physics does not care how much that hurts. There is a term in information theory called latency. It refers to the delay between sending a signal and receiving a response. On Earth, latency is measured in milliseconds. You click a link, the request travels to a server, the server responds, and the page loads. The whole process takes a fraction of a second. Increase the latency to a few hundred milliseconds, and the internet starts to feel sluggish. Increase it to a few seconds, and online gaming becomes unplayable. Video calls start to lag. Conversations feel awkward. Now imagine latency measured not in milliseconds or seconds, but in years. That is what interstellar communication is. A latency so extreme that the concept of interaction breaks down. You are not communicating. You are leaving messages. You are broadcasting into the void and hoping someone is still listening on the other end, and knowing that by the time they respond, if they respond, you will be a different person in a different situation with different problems. The isolation is absolute, not because the crew is physically alone, though they are, but because they are temporally alone. Cut off from the flow of events on Earth by a delay so long that causality itself becomes meaningless. You cannot influence Earth. Earth cannot influence you. The two timelines run parallel, intersecting only in the form of old messages arriving years late, carrying news that no longer matters. And yet, people will still send messages, because we are human, because we need connection, even when connection is impossible. The crew will send updates. Earth will send replies. Both sides will pretend that the conversation is real, that the relationship still exists, even though the relationship is functionally a historical artifact, a thing that used to be. Maintained now only through ritual and habit and refusal to accept that the distance has killed it. This is the echo, not the message itself, but the fact that the message arrives from a time that no longer exists. An echo of a voice that has already changed, already moved on, already aged or died. The farther you go, the louder the echo becomes, and the fainter the original voice. Until eventually you stop hearing anything at all. The messages stop, or you stop sending them, or you stop checking if they arrived. Because what is the point? What are you holding on to? A memory of a world that no longer exists, a connection to people who have become strangers, a version of yourself that died the moment the ship left orbit. The point of no return is not a place, it is a realization. The moment you understand that you are not coming back, not really, not to anything you would recognize, that the home you left is gone, not because it was destroyed, but because time ate it, because you were too far away to watch it change. And by the time you return, if you return, it will not be home anymore. It will be a foreign country that happens to orbit the same star. Some crews might handle that well. They might embrace the independence, build their own culture on the ship, decide that they are no longer representatives of Earth, but citizens of the ship itself. A new nation, a new people, separate, autonomous, free. Others might not handle it at all. The weight of the isolation, the finality of the separation might crush them, and there is no therapist to call, no support group. Just the crew, locked in a metal tube, trying to hold themselves together while the light years pile up behind them. And the worst part is that Earth will keep sending messages for years, decades. People will keep trying to stay in touch, keep trying to maintain the relationship, keep pretending that the distance does not matter. And the crew will receive those messages years late and realize that the people sending them do not understand, cannot understand, because they are still on Earth, still surrounded by other people, still connected. They have never been alone the way the crew is alone, and they never will be. The echoes of home are not comforting. They are reminders, reminders of what you left behind, reminders of what you will never have again, reminders that you made a choice, or a choice was made for you that cannot be undone. You are out here now, in the dark, in the silence, 25 trillion miles from anywhere that matters, and the only way forward is forward, toward the destination, toward Alpha Centauri, toward whatever waits there. Because going back is not an option, not technically, not emotionally, not in any sense that would satisfy the part of you that wants to go home. So you keep going. You keep sending messages even though the replies take years. You keep living even though the life you are living is disconnected from the rest of humanity. You keep hoping that the destination will justify the cost, that whatever you find at Alpha Centauri, whatever worlds orbit those stars, will be worth the silence, worth the isolation, worth the echoes. Because if it is not, if you get there and find nothing, or find something but realize it does not matter, then the whole journey was for nothing. A 42-year exercise in endurance that led nowhere, a message sent into the void that was never answered. But you will not know until you arrive, and arrival is still decades away, still trillions of miles ahead, still buried in the future behind layers of uncertainty and danger and the slow grinding passage of time. So you keep going, because stopping is not an option, and going back is not an option, and the only thing left is forward, into the silence, into the dark, toward the stars. And maybe, just maybe, when you get there, when the ship finally decelerates and the crew looks out the windows and sees an alien sun lighting an alien world, maybe the silence will break. Maybe the isolation will feel worth it. Maybe standing on the surface of a planet no human has ever touched will justify the cost, the years, the separation, the echoes of a home that no longer exists. Maybe. Or maybe you will arrive and realize that you gave up everything for a rock orbiting a star, a place no more meaningful than the one you left, a place that is just as empty, just as cold, just as indifferent. And the only difference is that this one is 25 trillion miles from anywhere you could call home. That is the gamble, that is the cost, and that is what waits at the end of the echoes. And the worst part is that Earth will keep sending messages for years, decades. People will keep trying to stay in touch, keep trying to maintain the relationship, keep pretending that the distance does not matter. And the crew will receive those messages years late and realize that the people sending them do not understand, cannot understand, because they are still on Earth, still surrounded by other people, still connected. They have never been alone the way the crew is alone, and they never will be. The echoes fade, the silence deepens. And after 42 years of coasting through the void, after 42 years of radiation and isolation and the slow grinding passage of time, the ship finally arrives, the engines fire. The crew wakes from whatever suspended state they have been in, or they have been awake the whole time and are now too old to remember what young felt like. Either way, they are here. Alpha Centauri, 3 stars orbiting each other in a slow gravitational waltz. And somewhere in that system, maybe, possibly, hopefully, there is a world, a planet, a place where humans could stand, breathe, live. That hope is why anyone would attempt this journey in the first place. Not for the accomplishment, not for the data, not to prove it can be done, but because somewhere in the back of every conversation about interstellar travel, buried under the engineering problems and the cost estimates and the physics, is a single quiet question. Is there another Earth out there? Another world where life could take hold? Another home? We already know the answer is yes, sort of. We know there are planets orbiting Alpha Centauri, not many, not a solar system full of them like ours, but at least one confirmed world and a few others that might exist if the data holds up. The confirmed one is called Proxima Centauri b. It orbits Proxima Centauri, the smallest and dimmest of the three stars, the red dwarf that sits slightly closer to us than the other two. Proxima b was discovered in 2016 using the radial velocity method, which measures the tiny wobble a planet induces in its host star as it orbits. The wobble is caused by gravity. The planet pulls on the star just as the star pulls on the planet. The effect is minuscule, but detectable if your instruments are good enough, and in this case, they were. Proxima b is roughly 1.3 times the mass of Earth, close enough to Earth-sized that it does not immediately disqualify itself as a potential habitat. It orbits Proxima Centauri once every 11.2 days. That is fast, 11 days to complete a full year. But it makes sense when you realize how close the planet is to its star. Proxima b orbits at a distance of about 4.6 million miles. For comparison, Earth orbits the Sun at 93 million miles. Mercury, the closest planet to our Sun, orbits at about 36 million miles. Proxima b is closer to its star than Mercury is to ours, much closer. Normally, that would be a problem. A planet that close to a Sun-like star would be scorched. The surface would be molten. The atmosphere, if there ever was one, would be stripped away by intense radiation. Nothing could live there, but Proxima Centauri is not a Sun-like star. It is a red dwarf, small, cool, dim. Its surface temperature is only about 3,000 Kelvin compared to the Sun's nearly 6,000. It puts out far less energy. So a planet can orbit much closer and still receive about the same amount of light and heat that Earth gets from the Sun. Proxima b sits right in that zone, close enough to its dim star that liquid water could exist on its surface, not guaranteed, but possible. That zone is called the habitable zone, sometimes called the Goldilocks zone, and it is the first thing astronomers look for when they search for potentially habitable planets. Not too hot, not too cold, just right, or at least not obviously wrong. The habitable zone is not a guarantee of life. It is not even a guarantee of habitability. It is just a range of distances from a star where temperatures allow liquid water to exist, assuming the planet has an atmosphere, which is a big assumption, but it is a starting point, a way to narrow the search, and Proxima b sits inside it. The problem is that we do not know much else about the planet. We know its mass, we know its orbital period, we know roughly how far it is from its star. That is it. We do not know if it has an atmosphere. We do not know what that atmosphere is made of, if it exists. We do not know if there is water on the surface. We do not know if the surface is solid or molten or covered in ice. We do not know if the planet is tidally locked, which means one side always faces the star and the other side is always dark, a common situation for planets orbiting close to red dwarfs. If it is tidally locked, one hemisphere could be blazing hot while the other is frozen solid, with only a narrow ring between them where temperatures might be survivable, or the planet might have a thick enough atmosphere to redistribute heat and create a more stable climate. We do not know. We do not know because Proxima b is too far away and too faint to study in detail with current telescopes. Detecting the planet at all was a feat. Characterizing it, figuring out what it is actually like, requires instruments we do not have yet. The James Webb Space Telescope can analyze the atmospheres of some exoplanets, but mostly large gas giants that pass directly in front of their stars from our perspective, creating a tiny dip in the star's light that can be studied in detail. Proxima b does not transit its star from our point of view. It does not pass in front, so we cannot use that technique. We are stuck with indirect measurements and educated guesses. But the fact that Proxima b exists at all is significant because it tells us that planets can form around red dwarfs. And red dwarfs are the most common type of star in the galaxy. Roughly 70% of all stars are red dwarfs. If red dwarfs can host habitable planets, then the number of potentially habitable worlds in the galaxy just exploded. We are not looking at a rare phenomenon. We are looking at something that might be everywhere. There are other planet candidates in the Alpha Centauri system. Data from various telescopes and observation campaigns have hinted at additional worlds orbiting Alpha Centauri A and Alpha Centauri B, the two larger stars in the system. None of those candidates have been confirmed reliably. Some were announced, then retracted. Others remain uncertain, sitting in the gray area between detection and noise. Confirming planets around nearby stars is hard because the stars are so bright compared to the planets. The light from the star drowns out everything else. It is like trying to spot a firefly next to a searchlight. The firefly is there, but good luck seeing it. Astronomers have developed techniques to deal with this. Coronagraphs block out the star's light, creating an artificial eclipse so the region around the star can be studied. Adaptive optics correct for the blurring caused by Earth's atmosphere. Radial velocity measurements track the wobble. Direct imaging tries to capture actual photons reflected or emitted by the planet. All of these methods work, but they work best on planets that are large, far from their stars, or orbiting dim stars. Proxima b was detectable because it orbits a red dwarf close enough that the wobble was measurable. A smaller planet, or one farther out, or one orbiting a brighter star, becomes exponentially harder to find. So we suspect there are more planets in the Alpha Centauri system. We hope there are, but we cannot confirm them yet. And even if we could, confirming their existence is not the same as confirming habitability. Habitability is a much tougher standard. To be habitable, a planet needs a few things. Liquid water is the obvious one. Every form of life we know requires water. Not just water in any form, but liquid water. Ice does not count. Water vapor does not count. You need liquid, which means you need temperatures and pressures that keep water in its liquid state. That puts boundaries on the planet's distance from its star and on its atmospheric pressure. Too far or too thin an atmosphere and the water freezes or evaporates into space. Too close or too thick an atmosphere and you get a runaway greenhouse effect like Venus, where surface temperatures hit 470 degrees Celsius and the pressure is 90 times Earth's. Second, you need an atmosphere, not just any atmosphere, a stable one. One that has oxygen if you want complex life. One that has greenhouse gases if you want the planet to stay warm. One that blocks harmful radiation. One that cycles carbon and nitrogen and supports weather patterns and ocean currents. Building and maintaining an atmosphere is not trivial. You need the planet to be massive enough that its gravity can hold on to gases. You need a magnetic field to protect the atmosphere from being stripped away by stellar wind. You need volcanic activity or some other mechanism to replenish gases that get lost to chemical reactions or escape into space. Earth has all of that. Mars used to have some of it and lost it. Venus has an atmosphere, but it is toxic and crushing. The balance required for a breathable, stable atmosphere is narrow. Third, you need the right kind of star. Not too hot, not too cool, not too violent. Stars that are too massive burn bright and die fast. A star 10 times the mass of the Sun only lives a few million years before going supernova. That is not enough time for complex life to evolve. Life on Earth took over 3 billion years to go from single cells to multicellular organisms. You need a star that sticks around. Stars that are too small, like red dwarfs, live for trillions of years, which is great for longevity. But they also tend to be active. They throw flares, massive eruptions of radiation and charged particles that can strip atmospheres and sterilize surfaces. Proxima Centauri throws flares regularly. Some of them are powerful enough that if you were standing on the surface of Proxima b during one, the radiation dose would be lethal. Maybe the planet has a thick atmosphere or a strong magnetic field that protects it. Maybe it does not. We do not know. Sun-like stars, yellow dwarfs like our Sun, sit in a kind of sweet spot, long-lived enough for complex life to evolve, stable enough that they do not throw constant tantrums, bright enough to provide energy, but not so bright that they burn out quickly. That is why most searches for habitable exoplanets focus on Sun-like stars or slightly cooler orange dwarfs. Red dwarfs are being studied more now because there are so many of them, but they come with risks. Risks we do not fully understand because we have never studied a planet orbiting one in detail. Then there is the question of what habitability even means. Habitable for what? For humans? For life in general? For microbial life? Or for complex ecosystems? Those are different standards. A planet could be habitable for bacteria and completely uninhabitable for humans. The early Earth was like that. Life existed for billions of years in an atmosphere with no oxygen. Oxygen only showed up after photosynthetic microbes started producing it as waste. If humans had been around back then, we would have suffocated. The planet was habitable, just not for us. When astronomers talk about habitable planets, they usually mean planets where liquid water could exist and where conditions might allow some form of life. Not necessarily life we could live alongside, not necessarily life we would recognize, just life. The assumption is that if life exists, even microbial life, that is significant, that is worth finding. And if a planet can support microbial life, maybe it could be engineered or terraformed over centuries to support human life. Maybe. The challenge of confirming habitability from Earth is enormous. You cannot just point a telescope at a planet and see if there are trees or oceans. Exoplanets are too far away and too faint. The best we can do is analyze their atmospheres, if we can detect them, and look for chemical signatures that suggest life. Oxygen in an atmosphere is a potential biosignature. On Earth, oxygen is produced almost entirely by living organisms. If you detect oxygen in an exoplanet's atmosphere, it is possible, not certain but possible, that something alive is producing it. Methane is another biosignature, especially if found alongside oxygen, because those two gases react with each other and should not coexist in large quantities unless something is constantly replenishing them. On Earth, that something is biology. Microbes produce methane. Plants produce oxygen. The two gases sit together in our atmosphere because life keeps making more. But detecting those gases in the atmosphere of a planet 4 light-years away is extraordinarily difficult. The James Webb Space Telescope can do it for some exoplanets, but mostly the large ones that transit their stars. Proxima b does not transit. We cannot use Webb's most powerful technique. We are left with less precise methods. Reflected light spectroscopy, where you analyze the light reflecting off the planet's surface and atmosphere. Direct imaging, where you try to photograph the planet itself. Both are possible in theory. Both are at the very edge of what current technology can achieve, and both require years of observation to gather enough data to say anything definitive. So when people ask if there is a habitable planet at Alpha Centauri, the honest answer is, we do not know. Proxima b might be habitable. It sits in the right zone. It has roughly the right mass. But it might also be a barren rock with no atmosphere, or a frozen wasteland, or a radiation-blasted hellscape constantly bombarded by flares from its violent star. We will not know until we send better instruments, or until we go there. And that brings us to the long-term vision, the idea that drives all of this, that humanity will not stay on Earth forever, that we are, by nature, explorers, wanderers, that the survival of our species might one day depend on spreading beyond this single fragile planet orbiting this single ordinary star. Because Earth is not permanent, the Sun is not permanent. In about 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, swallowing the inner planets. Earth will be gone. Life here will end. If humanity is still around, we will need to be somewhere else. 5 billion years is a long time. Long enough that worrying about it now seems absurd. But there are nearer threats. Asteroid impacts, supervolcanoes, climate collapse, nuclear war, pandemics, artificial intelligence gone wrong. Any one of those could wipe out human civilization or drive us to extinction. Spreading to other worlds, other star systems, is the ultimate insurance policy, not because it is easy or cheap, because it is the only way to guarantee that something survives. Carl Sagan called us a way for the cosmos to know itself. Stephen Hawking warned that we need to become a multiplanetary species if we want to survive long-term. Elon Musk has built an entire company around the goal of making humanity interplanetary, starting with Mars. The logic is simple. 1 planet is a single point of failure. 2 planets is redundancy. 10 planets, 10 star systems, 100 colonies scattered across the galaxy, and humanity becomes effectively unkillable. You can lose Earth and the species survives. You can lose entire star systems and the species survives. You become resilient in a way no single planet civilization can ever be. But getting there requires crossing distances that break every intuition we have about travel. It requires technology we do not have. It requires energy on scales we do not generate. It requires commitment across generations. And it requires finding places worth going to, worlds that can support us, or worlds we can adapt to support us. Alpha Centauri is the closest target. Proxima b is the closest potentially habitable world. If we cannot make that work, if we cannot cross 4 light years and establish a presence on a planet orbiting the nearest star, then the dream of spreading across the galaxy is just a dream, a nice idea that dies in the face of reality. And even if we succeed, even if we send ships to Alpha Centauri and land people on Proxima b and establish a colony, we are opening questions we have no good answers for. Who goes? Who decides? If the planet already has life, microbial or otherwise, do we have the right to alter it, to introduce Earth organisms that could outcompete or destroy whatever is there? Do we treat it like the new world, claim it, exploit it, build over whatever was there before? Or do we treat it like a nature preserve, observe but do not touch, leave it pristine? There is no international law governing interstellar colonization. There are treaties about the moon and near-Earth space, agreements that no nation can claim celestial bodies, that space is the common heritage of humanity. But those treaties were written when interstellar travel was pure fantasy. No one thought we would actually need rules for what happens when humans reach another star. Now, as the technology inches closer to feasibility, as missions like Breakthrough Starshot move from concept to planning, the questions become real. Who speaks for humanity when we reach another world? Who decides what we do there? Who protects the interests of potential alien life, if it exists, when no one on Earth has ever met it? The ethics are messy, The history of human exploration is not encouraging. Every time one group of humans has encountered another group or encountered a new land, the result has been exploitation, colonization, and often destruction. There is no reason to assume interstellar exploration would be different unless we make it different. And making it different requires thinking about it now, before we have the capability, before the decisions become urgent. Some argue that if we find a world with life, we should leave it alone. Study it, yes, learn from it, but do not interfere. Do not contaminate it with Earth biology. Do not extract resources or build cities or reshape the environment. Let it exist on its own terms. Others argue that the universe is vast and life is rare, and if we need a world to survive, we should take it. That survival of the human species is more important than preserving some alien microbes. That if the choice is between humanity and them, we pick us. Both arguments have logic, both have blind spots. The truth is probably somewhere in between, and we will not know where until we are standing on another world, looking at its sky and its soil, and deciding what comes next. That decision is still decades or centuries away, but it is coming. The technology will improve, the missions will launch. And one day, maybe not in this lifetime, but in some lifetime, a human being will step onto a planet orbiting Alpha Centauri, and the question of what we do there will stop being hypothetical. For now, the search continues. Telescopes scan the stars, data accumulates. New planets are found and catalogued and studied. The list of potentially habitable worlds grows every year, and with each discovery, the question shifts slightly. Not if we will reach the stars, but when, and what we will find when we get there, and whether finding it will answer the loneliness or just relocate it 25 trillion miles from home. The dream of a world beyond Earth is older than spaceflight, older than astronomy. It is baked into human nature. The urge to see what is over the next hill, the need to know if we are alone, the hope that somewhere out there is a place we could call home. Alpha Centauri is the closest step. Proxima b is the closest world. And everything we learn about it, every observation, every data point, every model is preparation for the journey that might one day follow. The one that carries us beyond the solar system, beyond the sun's light, into the territory of other stars, to see if the dream holds, or if the silence is all there is. But here is what we have learned. Here is what 25 trillion miles actually means when you strip away the poetry and look at the numbers with clear eyes. It means that with the fastest spacecraft we have ever built, the journey would take somewhere between 70,000 and 18,000 years, depending on whose estimate you trust and what assumptions you make about propulsion. Either way, the timeline stretches longer than recorded human history, longer than agriculture, longer than cities, longer than writing. You could launch a mission today, and every language currently spoken on Earth would be dead before it arrived. Every nation would be gone. Every person you have ever known or heard of would be dust. The ship would still be traveling, still coasting through the void, still decades or centuries from its destination. It means that even if we solve the propulsion problem, even if we invent fusion drives or antimatter engines or laser sails that can push a spacecraft to 10 or 20% of light speed, the journey still takes decades. 42 years at 10%, 20 years at 20%, and those numbers assume everything works perfectly, that the ship does not break down, that the crew survives, that the destination is worth reaching. One failure, one miscalculation, one piece of bad luck, and the mission ends in silence. No rescue, no second chance. just a metal tomb drifting through interstellar space, carrying the frozen remains of people who bet everything on a dream and lost. It means that communication becomes impossible in any real sense. 4 years for a signal to reach Earth, 4 more for a reply, 8 years round trip for a single exchange. By the time you get an answer, the question no longer matters. The world has moved on. You have moved on. You are talking to ghosts, to echoes of people who existed years ago. And they are talking to a version of you that no longer exists. The connection is broken not by choice, but by physics. And physics does not negotiate. It means that the human body, evolved for life on a planet with gravity and atmosphere and magnetic shielding, becomes a liability in deep space. Bones weaken, muscles atrophy, radiation shreds DNA, cosmic rays punch through hulls and flesh like bullets through paper. The environment is actively hostile in ways that no amount of technology can fully mitigate. You can shield yourself. You can carry medicine. You can build redundancy into every system, but you cannot eliminate the risk. You can only manage it. And over 42 years, over lifetimes spent in a metal tube hurtling through the void, the odds catch up. People get sick, people die, and there is no hospital to call. No doctor except the ones already on board. No treatment except what you brought with you. It means that the isolation is absolute. Not just physical, but psychological, temporal. You are cut off from the flow of human civilization in a way no one has ever been cut off before. The crew becomes its own world, its own society. And if that society fractures, if the crew turns on each other or loses the will to continue, there is no outside authority to intervene, no rescue, no mediation. Just the crew and the ship and the silence, and the distance growing behind them every second. It means that the destination, even if it exists, even if Proxima b or some other world in the Alpha Centauri system turns out to be habitable, might not be worth the cost. Because habitable does not mean welcoming, it does not mean safe, it does not mean home. It just means that liquid water could exist, and temperatures fall within a range that does not immediately kill you. The planet could still be barren, airless, covered in toxic dust, bombarded by radiation from a violent star. You could spend 42 years traveling to a rock that offers nothing except the fact that it is there. And even if the planet is habitable, even if it has an atmosphere and water and a climate that could support life, claiming it raises questions we have no good answers for. Do we have the right to colonize a world that might already harbor life? Do we have the right to alter it, to introduce Earth biology, to reshape it into something we can use? Or do we stand back and observe, accept that some places are not ours to take? The history of human exploration suggests we will do what we have always done. We will claim it, we will use it, we will justify it by saying survival matters more than ethics. And maybe that is true. Or maybe it is just the excuse we tell ourselves to avoid facing the fact that we are capable of destroying things we do not understand. This is the humbling horizon, the place where human ambition runs headlong into the limits of physics and biology and time, where the dream of reaching the stars collides with the reality of what that actually requires, and the reality is brutal, unforgiving, indifferent to how badly we want it to be otherwise. 25 trillion miles is not a challenge in the way climbing a mountain is a challenge. Climbing a mountain is hard, but it is finite. You can see the summit, you can measure your progress, you can turn back if you need to. 25 trillion miles is a different kind of problem. It is not just distance, it is a barrier built into the structure of the universe. A gap so vast that even light, the fastest thing that exists, takes over 4 years to cross it. And we are not light. We are slow, fragile, biological organisms trying to survive in an environment that was never meant for us. The rocket equation tells us that carrying enough fuel to reach meaningful speeds is impossible with chemical propulsion. The mass of the fuel exceeds the mass of the payload by factors so extreme that the whole concept breaks down. You end up needing a fuel tank the size of a planet to accelerate a ship the size of a house. And even if you solve that, even if you invent a propulsion system with perfect efficiency, relativity steps in and tells you that you still cannot reach light speed. That the closer you get, the more energy you need, and at exactly light speed, the energy required becomes infinite. The universe has a speed limit, and it is not a suggestion. Biology tells us that humans cannot survive decades of radiation exposure without consequences, that cosmic rays cause cancer, degrade neurons, damage cells at a fundamental level, that isolation drives people insane, that confinement breeds conflict, that even the healthiest crew will arrive at the destination weaker, sicker, older than when they left, if they arrive at all. Engineering tells us that building a ship capable of sustaining life for 42 years without resupply is extraordinarily difficult, that every system has a failure rate, that redundancy only buys you time, that eventually something critical will break and there will be no way to fix it, that materials degrade in vacuum, that seals fail, that electronics fry under radiation, that the longer the mission, the higher the odds that something goes catastrophically wrong. And physics tells us that communication across interstellar distances is limited by the speed of light, that there is no way around the delay, no shortcut, no trick. You are alone out there, functionally independent, cut off from Earth in every way that matters. And you have to accept that from the start, or the mission will break you. This is not pessimism, this is accounting. This is looking at the bill for what interstellar travel actually costs, and realizing that the price is higher than anyone wants to admit. The engineering challenges are solvable, maybe, given enough time, enough funding, enough breakthroughs, but the physical limits are not solvable, they are limits. Boundaries written into the fabric of reality, and no amount of cleverness or determination changes them. So why do we keep talking about this? Why do we keep designing missions, running simulations, building prototypes for ships that might not launch for decades or centuries? Why do engineers and physicists and astronomers spend their careers studying a problem that might not have a solution? Because the alternative is giving up. And giving up means accepting that we are trapped here, that the solar system is the boundary of human experience, that the stars will remain forever out of reach, no matter how advanced we become, and something in the human psyche refuses to accept that. We are explorers. We have always been explorers. We crossed oceans in wooden boats, not knowing what was on the other side. We climbed mountains because they were there. We went to the moon not because it was easy, but because it was hard, because the challenge itself mattered, because proving it could be done mattered. The same drive that pushed our ancestors out of Africa and across every continent on Earth is the drive that pushes us toward the stars. It is not rational, it is not cost-effective. It does not make sense from a purely utilitarian perspective, but it is who we are. And pretending otherwise, pretending that we will be content staying on one planet forever, ignores everything we know about human history. Carl Sagan once said that we are a way for the cosmos to know itself, that the atoms in our bodies were forged in the cores of dying stars, that we are made of star stuff. And if that is true, then reaching the stars is not just exploration, it is a kind of return, a reconnection with the processes that made us. The universe spent billions of years building the conditions for life. Life spent billions of years evolving intelligence. Intelligence built technology. And now technology is reaching back toward the stars, trying to close the loop, trying to understand the origins, trying to find out if we are alone or if the process that made us has happened elsewhere, on other worlds, around other stars, in other galaxies. That question, the question of whether we are alone, drives much of the interest in interstellar exploration. Because if life exists on Proxima b, if we land on that world and find even single-celled organisms living in the soil or swimming in a subsurface ocean, it changes everything. It means life is not a fluke, not a cosmic accident that happened once and only once. It means the universe makes life, that the conditions for life are common enough that it arose independently on at least two worlds. And if it arose twice, it probably arose thousands of times, millions, maybe more. The galaxy could be full of life, not intelligent life necessarily, not civilizations, but life, biology, chemistry turned self-replicating. That alone is profound. And if we find nothing, if we search Proxima b and find a barren rock with no atmosphere and no water and no hint that life ever existed there, that is also profound. Because it suggests that life is rare, fragile, dependent on circumstances so specific that even a planet in the habitable zone of a nearby star does not guarantee it. That Earth is special in ways we do not fully understand, that we are, if not alone, then at least extraordinarily uncommon. And that makes protecting the life we have here even more urgent. Either answer matters. Either answer is worth the effort of finding out. But finding out requires going there, or at least sending something there. A probe, a telescope, a mission capable of gathering data and sending it back. And every one of those options requires solving problems that currently do not have solutions. Breakthrough Starshot, the privately funded initiative to send tiny laser-propelled probes to Alpha Centauri, is the closest thing we have to a realistic interstellar mission plan. The idea is elegant. Build a fleet of small spacecraft, each weighing about a gram, attach them to reflective sails, and accelerate them with a ground-based laser array. Reach 20% of light speed. Arrive at Alpha Centauri in about 20 years. Take pictures, gather data, send it back. The entire mission, from launch to data return, could happen within a human lifetime. That is extraordinary, if it works. The challenges are formidable. Building a laser array powerful enough to accelerate the sails requires technology we do not have. Keeping the beam focused over millions of kilometers as the probes accelerate is an unsolved problem. Building a spacecraft small enough and light enough to be accelerated by light pressure, but robust enough to survive the journey, is an engineering nightmare. The probes have to carry cameras, transmitters, power sources, and enough intelligence to orient themselves and send data back across 4 light years. All in a package weighing about a gram. It is barely possible, and barely possible is not the same as likely, but the fact that serious scientists are working on it, that funding exists, that the physics has been checked and rechecked, tells you something important. The problem is not hopeless. It is just hard, and hard is something humans are good at. We have solved hard problems before. We split the atom. We built machines that think. We sent robots to other planets and landed them safely and drove them around for years. We built telescopes that can see galaxies formed when the universe was a fraction of its current age. Hard is not the same as impossible. The gap between where we are and where we need to be is vast, but it is not unbridgeable, not with time, not with effort, not with the willingness to commit resources across generations. The Apollo program took less than a decade from announcement to moon landing. That was with 1960s technology and Cold War urgency. Imagine what could be done with modern technology and sustained long-term commitment. Not a decade, not a presidential term, a century, multiple generations. The kind of project that your great-grandchildren complete. That is the scale required for interstellar travel, and we have never built anything on that scale. We have never had to. But the universe does not care about our timelines. It does not care that building a starship takes a century or that the crew who launches it will die before it arrives. The distance is still 25 trillion miles. The speed of light is still the speed of light. The laws of physics do not bend because we find them inconvenient. They just are. And if we want to reach the stars, we have to work within those laws, or find ways around them that do not break them. Some physicists have speculated about shortcuts. Wormholes, warp drives, ways to manipulate space-time itself so that the distance becomes irrelevant. The math allows for it, sometimes, barely, in very specific circumstances that might not exist in the real universe. But even if they do, even if exotic matter or negative energy or some other requirement turns out to be possible, we are centuries away from being able to manipulate it. Warp drives are not on the table, not now, probably not ever. They are the kind of thing you talk about when you have exhausted every realistic option and are looking for miracles. And maybe that is what interstellar travel requires, a miracle. Or at least something that looks like one from where we stand today. A breakthrough so profound that it changes the entire conversation. Controlled fusion, room temperature superconductors, antimatter production at scale. Artificial intelligence capable of running a starship autonomously for decades. Any one of those would help. All of them together might be enough. But waiting for breakthroughs means waiting, and waiting is not the same as working. Breakthrough Starshot is working. NASA's interstellar probe concepts are working. The scientists studying exoplanets, characterizing their atmospheres, mapping the stars, are working. The engineers designing better propulsion systems, better shielding, better life support, are working. Progress is being made, slowly, incrementally, in ways that do not make headlines, but it is happening. And one day, maybe not soon, maybe not in this century, but one day a ship will leave Earth and set course for Alpha Centauri. Maybe it will be a tiny probe, no bigger than a postage stamp. Maybe it will be a crude vessel carrying a dozen people willing to spend their lives in transit. Maybe it will be a generation ship, a floating city designed to sustain a population across multiple lifetimes. We do not know what form it will take, but it will happen. Because humans do not stop. We do not stay put. We push. We explore. We reach for things we cannot touch and figure out how to touch them anyway. That is the enduring dream. Not that interstellar travel is easy. It is not. Not that the challenges are trivial. They are not. But that despite the distance, despite the radiation, despite the isolation and the silence and the crushing weight of cosmic indifference, we will go anyway. Because the horizon is there, because the stars are there. Because the question of what lies beyond will not leave us alone until we answer it. The humbling part is not that the journey is hard. The humbling part is realizing how small we are, how young, how fragile. We are a species that has been technologically advanced for maybe a century. We have had spaceflight for less than 70 years. We have been studying exoplanets for about 30. On cosmic timescales, we are infants, barely aware of the universe around us, barely capable of reaching beyond our own atmosphere. And yet we look at the nearest star, 25 trillion miles away, and we say we will go there. We will cross that distance. We will figure it out. The confidence borders on arrogance, but it is also the only reason we have gotten this far. Alpha Centauri is not the destination. It is the test, the proof of concept. If we can reach the nearest star, we can reach others. If we can establish a presence on a planet orbiting another sun, we can do it again and again. And eventually, the distance stops being a barrier and starts being just another obstacle. One more thing to solve, one more challenge to overcome. But for now, the distance is absolute, 25 trillion miles, 4.24 light years, 70,000 years with current propulsion, 42 years if we can reach 10% light speed, and all of that assuming nothing goes wrong, assuming the technology works, assuming the crew survives, assuming the destination is real. The horizon is humbling because it reminds us that the universe is bigger than we are, older, more patient. It was here before us, and it will be here after us. And it does not care whether we reach the stars or stay home. The stars will keep burning either way. The galaxies will keep spinning. The universe will keep expanding. Our presence or absence makes no difference to any of it. But it makes a difference to us, and maybe that is enough. And maybe that is enough, because here is the truth that sits at the bottom of all of this. The distance to Alpha Centauri has not changed in the entire history of the human species. It was 25 trillion miles when we were living in caves. It was 25 trillion miles when we built the pyramids. It was 25 trillion miles when we split the atom and walked on the moon and launched Voyager into the dark. And it will still be 25 trillion miles 1,000 years from now. The universe is not getting smaller. The stars are not moving closer. The gap is permanent. What has changed is us. What might still change is us. We went from wooden boats to spaceflight in less than 500 years. From the first powered flight to landing on the moon in 66 years. From discovering the first exoplanet to cataloging thousands of them in 3 decades. The distance to Alpha Centauri has not moved. But we have, and we are still moving. The journey is terrifying. The cost is staggering. The odds are not good. But the fact that we are even capable of asking the question, of calculating the distance, of designing missions that might one day cross it, says something about what we are. We are a species that looks at impossible and treats it like a dare. 25 trillion miles. 42 years if everything works, 70,000 years if it does not. Either way, the distance is waiting, the stars are waiting. And somewhere, in a lab or a workshop, or a mind that has not been born yet, the solution is waiting too. Not because the universe owes it to us, but because we refuse to stop looking. And refusal, it turns out, is the only tool that has ever moved mountains, or crossed voids, or carried fragile creatures